All right, welcome back, everybody. Welcome back from lunch. Did anybody have a 7-layer burrito because of the 7 layers of OSI? No? Tim was like, oh, I missed that chance now. That's okay. Tim, tomorrow when we talk about the Caesar cipher, you can have a Caesar salad tomorrow for lunch. It would be funny if it was like a themed buffet based off of the content of the day. Absolutely. That'd be awesome. Okay, welcome back. Now that we had this conversation about how networks work as far as, say, the US Postal Service goes, let's go ahead and start putting some technology around these things. So in our map earlier of this network of postal service sorting centers, we had put technology around that. We said, well, now let's imagine these are ISPs, and ISP to the ISP, the backbone of the internet. Though it doesn't look like it at first, this diagram is literally the thing that we just looked at. Of course, now it's in technical terms, it's computers, and it's different computing networking devices connected together. But what we're going to do is we're going to take that same scenario that we saw earlier with the US Postal Service, and let's just put it into a computer network. In this network, we have 3 different sub-networks. There's sub-network number 1, sub-network number 2, sub-network number 3. And then we've got some networking devices, something between them that connect them together. And we also have a 4th one. This 4th one here isn't a sub-network of ours. This 4th one is the internet. And so what I want to do is imagine this is just 3 floors of a building, and I have a subnet on 1, subnet on floor number 2, subnet on floor number 3, and my goal is to send a packet of information from system 2 on subnet 1 going to system 2 on subnet 3. They are not directly connected together. There are some things in between them. So let's talk about the path that this information would take going from system 2 on subnet 1 to system 2 on subnet 3. First, system 2 on subnet 1, the sender of the data, asks itself a question based on the address of the destination. Is that destination on the same network as me, or is it on a different network? Turns out, now we're going to talk about how it determines that a little bit later this afternoon. But let's say that system 2 on subnet 1 says, no, this receiver is not on my local network, and so I cannot send it directly to them. I need to send it to my gateway. My gateway is the gate out of my subnet. So it asks the question, hey, who's my gateway? Now it asks that question of all of the computers around it in that subnet, and all the computers hear this question, only one responds, the gateway. The gateway says, I am your gateway. And so then this system is going to remember that answer for a short period of time, and it's going to send that information to network 1's gateway. Now, network 1 gateway has received this information. It's not meant for them. They know it's not meant for them. They look at the address and says, this isn't for me. Somebody's asking me to deliver this for them, to forward it on. And so now the subnet 1's gateway has this information. It asks, based on the address, it says, am I directly connected to the network for system 2 on network 3? No, I'm not. So I send it to my gateway. In this case, we call it an intermediate gateway because it's a gateway between the other gateways. And so that system asks, hey, who is my intermediate gateway? And then it gets one response. I am the gateway from the intermediate. The subnet 1. What did I eat for lunch? Because I'm just having a hard time with my words here. Subnet 1's gateway remembers that answer for a short period of time and sends the packet along its way. All right, cool. Now the intermediate receives this information, and based on the address that's going to, the intermediate says, oh, I know where this goes. This goes to network 3 gateway. So which one is my network 3 gateway? And so the intermediate then asks, hey, who is my network 3 gateway? Network 3 gateway responds, I am, and remembers, the intermediate remembers that for a short period of time and forwards the information on its way. Now network 3's gateway receives this and says, oh yeah, based on that address, I know where that goes. That goes to system 2 on my network. And so now it is going to ask, hey, who is system 2 on my subnet 3 network? It asks the question to everybody. We get one response back. System 2 says, I am system 2 on this network. That gateway remembers that answer for a short period of time and forwards that packet of information on. And congratulations, we finally got the information to system 2 on subnet 3. But that was a lot of repetition. That's gotta be a mistake, right? No, it's actually by design. All of these steps happened, but they happened at roughly the speed of light. And so when system 2 subnet 1 sent the information, almost instantaneously, system 2 and subnet 3 received that information. It didn't take long. Now, system 2 on subnet 3 needs to return a response to system 2 on subnet 1. And it's basically that response is going to take the same path back. There's all the steps in between of who's my gateway, all of that going back to its original destination. And that's one of the reasons why these systems remembered that information for a short period of time, because maybe I'm going to use that real soon here. Now, there's 2 different ways to look at this flow of traffic. First, there's the logical flow of the data. And the logical flow is that system 2 on subnet 1 was sending data to system 2 on subnet 3. And so the logical flow says who the sender is and who the receiver is. But the physical flow is how that data actually flowed through the cables between the connections, between the systems with those connections, shall I say. And so that's the physical flow of how the data actually traversed the network. Now, let's talk about that intermediate. That intermediate was a decision point where we were based on this information that was in that packet, its destination address. That control point had a list of other networks on its networking device that basically said, well, for subnet 1 addresses, I send them out one of the interfaces. For subnet 2, I send them out a different physical interface. For subnet 3, I send them out a different one. And if it's not bound for any of those subnets, it's bound for someplace else out on the internet, then it would send it out to the interface for the internet. But that control point is going to look at the address, and it's going to compare that address to a bunch of settings on its in a table that says which direction we should physically send this packet. Network 1's gateway, all it was doing was allowing packets to come into that subnet 1 and allowing packets to leave subnet 1, going out to the rest of the network. Subnet 3's gateway, same thing. It's just allowing packets to go in and out of that network. But this intermediate needs to make a decision as to which direction, because it had a choice. Which way do I go? Now, what I've just described is a local area network. Local area networks, or a LAN, is in a limited geographic area, and it's almost always using the Ethernet protocol. So at layer 2, and it can be one subnetwork, or it could be multiple subnetworks. For example, in this room, we are all connected to the SEC 301 Wi-Fi hotspot, right? And so aren't we a LAN in this room? We fit that definition. It's a limited geographic area, and we are using the Ethernet protocol. We're going to talk about Ethernet later, but we're a LAN here. But now, the room next to us, that management course, aren't they a LAN? Yeah, by definition, they are a LAN. And this forensics course on the other side of us, aren't they a LAN? Yes, they're a LAN as well. Well, wait a minute. Couldn't we consider this hotel to be a LAN? Isn't it a local area network? It's in a limited geographic area, and we're using the Ethernet protocol. Okay, so this hotel could be a LAN as well. Now, when does a local area network become what we refer to as a wide area network? A wide area network is where it's not a limited geographic area, it's a large geographic area. And it's not using Ethernet, it's using some other protocol. Now, typically, a LAN stops being a LAN and becomes a WAN when you're using an ISP for your connection out to the other networks. That's usually the case. Now, Hilton is the hotel that we're staying at. It's a Hilton branded hotel. And when I showed up on Sunday to check in, they said, "Oh, welcome, Doc Blackburn. Thanks for being a Diamond member." So then they knew me. They know me? How did they know me? And how did they know I was Diamond status? Well, this Hilton, the Hilton brand, has lots of Hilton branded hotels around the world. And each time I stay at a Hilton branded hotel, they know me as Doc Blackburn, and that they know that I've stayed at a lot of different locations. So Hilton has hotels around the world, and each physical property, isn't that a LAN? Yeah, and then they must have a data room, what is the word I'm looking for? Data center. A data center with a server that keeps my information on at some location. And in that data center, that would be a LAN as well. But each one of these Hilton properties with their LAN, they use their internet connection to grab that data, to change the data. If I need to update my address, oh, I moved, and so here's my new address. Each LAN is connected together through their ISP. And so each LAN of Hilton connected together becomes a WAN, because now they share information from this LAN to another Hilton property. I was at a Hilton property in London last week, and I'll be staying at another one, I'm sure, at, I think in, where am I going next? Melbourne. And I think it's a Hilton property over there. And so each one of those LANs across the world are connected to make this WAN. And then the WAN to end all WANs is the internet. And we used to say the internet is a global network. Well, guess what? There's IP addresses on devices in the sky, in satellites. There's IP addresses for lunar rovers on the moon and Mars. And so the internet is not just global anymore, it's interplanetary at this point. Isn't that cool how far the internet scaled? We're literally on multiple planets now. So I'd say that, I guess, is the widest of the wide area networks. Now, how do I connect all of these pieces of equipment together to make this network? I need some fundamental networking equipment. The first is called a network interface card, or a NIC. And just like pin number, I don't ever want you to say NIC card, because they're saying network interface card. Don't say that. That hurts my brain when people say NIC card. Now my NIC has two addresses. There is a hardware-based address, and then there is an IP address that is associated with my NIC. So now, my NIC with this hardware address is a unique address to this network that identifies me as this computer on this LAN. Now, my address is unique for my computer, and everywhere that I go in the world, it's the same hardware address. We call it a MAC address. MAC stands for Media Access Control. It has nothing to do with Apple computers. But this MAC address follows me wherever I go. Well, how in the world do I know that I have a unique address here when all of you have unique MAC addresses as well? How did we make sure that everybody had their own unique MAC address here in this room? It's because every NIC that's manufactured gets a unique address. It's actually a 6-byte address that is noted in hexadecimal characters. Oh, hexadecimal comes back. So you guys know that we've got, these are just bytes of information, right? 2 hexadecimal characters is a byte. So there's a byte and a byte and a byte. 1, 2, 3, 4, 5, 6. A MAC address is a 6-byte address. And it will be notated in hexadecimal, and the bytes will typically either have a colon or a dash between them. Now, the colon or the dash, that doesn't exactly actually exist in the address. That's just us humans trying to differentiate the bytes, right? So now, every manufacturer of these network interface cards are given a 3-byte unique combination that describes that manufacturer. So the first 3 bytes describes the manufacturer of the NIC, and then the second 3 bytes, each of those manufacturers use to make every NIC that they make unique. So therefore, in theory, every single MAC address in the world should be unique because the manufacturers are using their OUI, organizational unique identifier. And as long as they make all of their devices have unique addresses for that first 3 bytes, that's the same for them, every address in the world should be unique. So you all came with your computers, with your NICs, and we put these all on the same network. There were no collisions where we had the same address because there's no 2 addresses like it in the world. All right, good. So far, so good. Now, the other address that my computer needs to have to participate on the network is the IP address, that internet protocol address. Now, unlike my MAC address that stays the same wherever I'm at, my IP address changes based on the network that I'm on. So last week, I was in London. My MAC address was in London with my computer, but I got a London-based IP address. I packed up my computer and I flew from London Saturday back home, and I turned my computer on, plugged it into my Denver network. My MAC address was still the same, but my IP address was now a Denver-based IP address. And then I packed up my computer Sunday and I brought it here. My MAC address followed the computer. I have the same MAC address no matter where I'm at in the world, but my IP address has changed to a Washington, D.C. based IP address. And the same when I go to Melbourne, and then from Melbourne to Virginia Beach, and then from Virginia Beach back home to Denver, my MAC address follows me everywhere I go. The IP address changes over time. Now, why do we need those 2 IP addresses? My MAC address is my unique identifier on this subnet. And so we know that I'm a unique identity here just simply because my number is unique. But it doesn't tell other computers where I'm at physically in the world. My IP address is needed so that we know where to geographically send that. Remember that least cost route where we need to get geographically closer to its final destination? The IP address is how we determine that. Now, what type of network equipment do I need to keep track of these addresses? There's switches and routers. Now, going back to our network diagram, you had seen that there was different types of shapes for these networking devices. Some of them were square and had 2 arrows pointing in one direction, 2 arrows pointing in the other. When you see that icon, that means that it is a switch. And then when you see those circles with 2 arrows pointing in, 2 arrows pointing out, those are what we refer to as a router. Now I have a new name for that gateway. That gateway is a router. And we are going to use those terms synonymously here in class. They essentially, for all intents and purposes at the level of explanation here, they're essentially the same device, right? Now the switches will keep track of those hardware MAC addresses. So let's say this device right here is a switch. I plug one end of the cable into the switch. I plug the other end of the cable into my computer. The switch is going to sense, oh, there's a computer at the other end. And through the Ethernet protocol, layer 2, the Ethernet protocol is going to say, hey, there's a computer over there. What's your address? And my computer is going to say my address is, and it gives this switch the MAC address. And now the switch will remember every single time it receives a packet meant for the for my MAC address, it knows to send it out this physical interface. So the switch keeps track of that on what they call a CAM table. So now, if you're taking notes in your book, a good time to write in your book is right now, where next to switch, write layer 2, because that's the Ethernet protocol, and that is where in the OSI stack switches operate, is at layer 2. But now the IP address that changes based on where I'm at geographically in the world, those are maintained by routers. The routers are devices that they look just like this, but it has a different job. It's working at a different layer. The routers are keeping track of IP addresses. And so it will forward traffic based on that IP. Now, because the IP address is at layer 3 of the OSI model, right next to router, go ahead and write the word layer 3. And so that'll help you when you take the exam. Now, every single device on my network is going to have an IP address and a MAC address. The MAC address that they brought onto the network and the IP address which was assigned to them on that network. And so now we can see I've got devices like 10.1.1.1, that's the IP address, and here's its MAC address, and 10.1.1.2, 1.3, 1.50, 1.51, all of these devices are connected to the switch. The switch keeps track of the MAC addresses for each one, and the router keeps track of the IP addresses for each one. Now notice the router is also a device on the network as well. So the router gets its own MAC address because it has a NIC in it, and it also gets an IP address because we have to know what is the IP address of that router we're forwarding our packets to based on that IP address. Now, I have a local area network. This router also allows traffic to flow out of my network or other traffic coming from outside the network flowing in. So the other side of the router, you'll see also has a MAC address and an IP address, and that's for another network. Which network we haven't defined here, but you see that router is going to allow traffic to flow into the subnet and flow out of the subnet. And these are all connected through a switch in the format of the star topology. The star topology is just simply, it's a bunch of cables plugged into one device in the center, and we've got all of these devices around that switch, and it kind of looks like a star. And so that's why it's called a star topology. Now, let's talk, go ahead, Michelle.
Router has its own IP server, switch not have its own.
Great question. So Michelle just asked the question, the router has its own IP address and its own MAC address. What about the switch? The switch is, for all intents and purposes, is pretty transparent on the network. It doesn't have its own MAC addresses. It doesn't, it just keeps track of MAC addresses for these devices. It doesn't have an IP address. Now, with that being said, some enterprise level switches where the network administrators are programming the switch, those switches do have IP addresses, but the IP address is just for the interface to configure the switch. It's not an IP address on the network. Yeah, good question. MJ. The switch, yeah, to be clear, the switch does not have MAC addresses. The switch only keeps track of other people's MAC addresses. So if I want to send a packet from, and we're actually going to do this in a little bit, if I need to send a packet of information from this machine, because this is the second machine on subnet 1, so that's that 1.2, the 1 here is the network, 2 is that host on the network, that device is going to send from their MAC address to the MAC address of the router. And the switch needs to know what everybody's MAC address is, but the switch itself doesn't have a MAC address. It's just a conduit for these devices to talk over those MAC addresses. Yeah, great question. Cool, so now let's go ahead and talk about why we need these two addresses. The MAC address is going to describe every hop along the way. From system 2 subnet 1 to system 2 subnet 3, there's a gateway in between them, this network 1 gateway, and then there's an intermediate gateway, and there's a network 3 gateway. What we're doing is the switches are going to forward that information going from 1.2 to 3.2. So the IP address routing is from 10.1.1.2 to 10.1.3.2. That's my logical flow, but my physical flow is I at system 2 subnet 1 needs to send it to my gateway. And so I am forwarding this packet to the MAC address of the gateway. And then gateway 1 forwards it to the MAC address of the intermediate gateway. Intermediate forwards it to the MAC address of network 3's gateway. Network 3 gateway forwards it on to system 2 on subnet 3. And so while the IP addresses describe specific geographic locations where I am sending data from this computer going to this other computer, the MAC address keeps track of every hop to hop to hop to get there. And so it defines that physical flow. Now we saw a question, Michael said, are those private or reserved IP addresses? To answer your question directly, Michael, yes. We haven't quite gotten that far. So for those who don't understand the question, just go ahead and erase that out of your mind. We will talk about IP addresses and private IP addresses in a little bit. But to answer your question, Michael, absolutely, those are private addresses. This 10 dot format, there's a reason why we're using it. We'll talk about that later. So I can send data from one IP address to another one by forwarding based on MAC address. Now, let's go ahead and talk about how we actually put those two addresses together, how we map an IP address to a MAC address. Because if my computer is moving from network to network and they assign an IP address to my NIC and I have a unique MAC address, how do we bridge those two addresses? It's called the address resolution protocol. The address resolution protocol is where we were asking that question, hey, who is the gateway? And you'll see that system got this response, I am the gateway. So the ARP protocol is just simply some information of the question, hey, who is that gateway? What it's literally asking is, I know your IP address because it's been defined in my network settings. What I don't know is what your MAC address is. So could you tell me what that MAC address is? Now we've got slides on these things, but rather than just doing slides, let's go ahead and do a live demo. You guys want to do a live demo? Let's look at the information itself. I've got a tool called Wireshark here, and you're going to be using Wireshark later in lab. So this is a good first demonstration of a new tool we're going to use later today. Wireshark allows me to look at network packets, network communications that's flowing in binary, ones and zeros across the network cable. My NIC is going to capture those ones and zeros. That's called a sniffer. When the NIC takes a copy of the ones and zeros and then sends them to Wireshark, Wireshark is a protocol analyzer, and it's going to interpret those ones and zeros based off of the RFCs. It will tell me what the MAC address of these packets are and the IP addresses and all of the other header information that we saw at layers 2 and 3 and 4. So what I've got here is actually a packet capture that I already made. This particular packet capture wasn't something I grabbed right now. I just saved in a file so I could show you guys. And let me show you these 3 windows that we have in Wireshark. You'll see that there are 4 lines up top here. Those 4 lines, each line represents 1 packet. Now, the next window here is the details of each one of these packets. For example, I'm going to click on packet number 1, and you notice when I clicked on packet number 1, the information in the second window changed. And actually the information in the third window changed as well. But what's that down below there, guys, in the third window? It's hexadecimal characters, which we know is just simply bits. Okay, so now I know that there's bits behind these things. What do those bits say? Wireshark is going to tell me. This is at Ethernet. It's layer 2. There is a destination address of, that's a weird MAC address. It's all Fs, which means the bits are all 1s, right? So is that a valid MAC address? Technically, it's not. It's a special address. Do you know what that address is? When a switch receives a packet going to a MAC address of all Fs, what the switch says is, oh, that's a broadcast. I send that to everybody plugged into the local switch. And so when it gets a MAC address of all Fs, it says, yeah, that's everybody. So it makes multiple copies of the packet and sends it to everybody connected to that switch. That's what's called a broadcast. Everybody received it that's connected to that switch. Now, we can also see that there is a source MAC address. This source MAC address is the sender. Whoever sent packet number 1 here, that's this person. Who's the receiver? Everybody. And so when this device sends that packet from its MAC address to everybody on the local switch, we all see a copy of that packet and we all know whose MAC address it came from. All right, so we all saw the packet and we also see who it came from. Now, let's go ahead and open up the next layer here. You can see that's the Ethernet layer. Now let's open up address resolution protocol. And the address resolution protocol is just simply a system of asking, hey, I am looking for a certain IP address. I need you to tell me what their MAC address is. Now notice the sender is the one who sent the packet at the Ethernet layer. That's me, and I am at this IP address. And then I'm asking everybody, I need to find the IP address listed here. Would you please tell me that MAC address? Now, this is an invalid MAC address as well, right? This one is set to all 0s. That's a special placeholder that says, I don't know the answer to this question. Could somebody fill in the blank? We didn't leave it blank because we have to have bits there, but the bits are all set to 0s, right? Basically saying, hey, everybody, I'm doing roll call here. Is Kim here? Kim, are you here? This is where you say, I'm here. Kim says, I'm here. All right, so basically what I've just done is broadcast to the class. Hey, I need to know who Kim is. Then Kim responds. Now, let's go ahead and go to the response. You'll see packet number 2 is now the sender at that 10.1.0.2. So the person who received this broadcast, everybody received it, but the person who received it, whose IP address matched that request, it's Kim. Kim says, yes, I am here. Here's my MAC address. All right, so now I broadcast the request, but Kim sends the response directly back to me. So you'll see that she sent it to my IP address and my MAC because my IP address and my MAC address was in the request. So I broadcast to everybody, hey, everybody listen, is Kim here? And then you all heard it. Kim responds, yes, I'm here. And so now I know who Kim is. Does anybody see? That's a whole ARP protocol. Does anybody see anything that looks like security there? Is there any security there whatsoever? Any field that even says security? It's nothing. So question for you. What if I ask the question, hey, is Kim here? And then I get two answers back. Kim says, yes, I'm here. But let's say Jake says, yes, I'm Kim, I'm here. Ooh. If I ask the question to everybody and I get two responses back, and I could, right? I mean, Jake can respond to that. Who am I going to believe? According to the ARP protocol, which one should I believe? I'm going to believe the first one that I got back. So all Jake needs to do what we call an impersonation attack is Jake just needs to be listening for that question. And then all he has to do is answer faster than Kim. That's called an ARP cache poison attack. And remember yesterday when we had that password cracking tool, Kane, and I said, remember this little yellow button, because we're going to talk about it tomorrow. That's that little yellow button. All I have to do is hit that button on Kane. And do you know what's going to do? Kane listens on the switch for all these ARP requests, and it just replies gratuitously to all of them. And it says, so somebody says, is Kim here? I'm Kim. Is Jake here? I'm Jake. Is Rennie here? I'm Rennie. It just responds to all of those. Now, let's say Kim was my gateway out of the network. And so I asked, hey, who is my gateway? My gateway is Kim, and I get two responses back. Jake responds faster than Kim. Jake says, I'm Kim. Where am I going to send my packets leaving the network? I'm sending them to the MAC address of Jake. Do I have any way of knowing that that happened? There's no way of knowing that that happened. And so let's review what we learned so far here. I know that Jake can do it. And I know that I can't reasonably stop him from doing it. There really is no reasonable way to stop that. So what must I assume is happening at all times? I'm going to assume that evil Jake is doing this. There's no security built into these protocols that govern the internet. I told you that earlier today. Does anybody not believe me at this point? There's no security there, none whatsoever. So that's our first lesson in network security. There is none. We start with zero, and we have to find some other way to build that trust on this untrusted network. Now, I do have a little bit of good news. It's a little bit a ray of sunshine in this cloud. The ARP cache poison attack that I've just described cannot be performed over the internet. Jake has to be on my local network in order for this to happen. That's the good news, but it's just a little ray of sunshine, because day 4, when EvilDoc shows you how to attack a network, EvilDoc is just looking for a system in your subnet. And so maybe Jake isn't physically here in this room. Jake has just compromised somebody's machine. And so now Jake is on our network because his malware is on our network, and his malware is doing all of this. So Jake doesn't have to be present. He just has to control a machine that's present on the network. Whew, boy, that was rough, wasn't it? It gets worse from there, folks, because what we're going to do now, we have just gone from layer 2 MAC addresses up to layer 3 IP addresses. What we're going to do is spend the rest of the afternoon talking about layer 3 and layer 4 communications. So we're just working our way up this stack. So the rest of our discussions today will be layers 3 and layers 4. and a few layer 7 protocols, right? So we're just working our way up that OSI stack. With the layer 3 header, it contains the sending IP address and the receiving IP address. And just like a letter that we put in the mailbox, it only defines who that sender is and who that receiver is. It doesn't tell the postal worker, hey, take that down to the post office, and from the post office, take it to the sorting center and all that. No, we just say, this is the final destination. You figure it out. So IP allows us to have this network equipment figure that out. It's a best effort protocol. Based on that address, we need to get to its final destination. Now, IP doesn't guarantee that the packets get delivered. If there's any errors, it doesn't notify you of them. It doesn't correct them. It just fails. Bleh, I couldn't do it. Sorry, didn't make it. So now, IP is just focused on that sending IP address and the receiving IP address. How do we get the packet from one location to another? The most common version of IP on the internet today is IP version 4. There is IP version 6 as well. And yes, many people on their internal networks are implementing IP version 6 on their internal networks. But we're talking about the internet here. And the internet is almost still, the majority of the traffic is all IP version 4 traffic. So we're just going to, I'm acknowledging that version 6 exists, but version 4 is the workhorse of the internet today. And it's going to be for quite some time, because even though IPv6 exists, you know how old IPv6 is? It's the new protocol. How new is IPv6? Well, it was ratified in 1998. Where Windows 98, that was the operating system. That's the bomb. And Macs look like that thing. Gran Turismo with its graphic was amazing. Wow. And Adam Sandler and Drew Barrymore, they were young, and Adam Sandler was a wedding singer back in 1998. Yes, this version 6 protocol is old enough to drink, yet it still is not the majority of the traffic on the internet today. So I am going to make the assumption at this point that IP version 4 is still going to be the workhorse of the internet for a long time to come yet. Because in order for two computers to communicate across the internet to one another, remember, they have to use the same protocol. And so if your server that you're contacting is using IPv4, guess what you have to use? IPv4. With my IPv4 machine, I cannot contact directly an IPv6 machine. It just doesn't work. They're two different versions. And remember, we have to have the same protocol stack for both computers, or we won't be able to communicate. Now, with IPv4, we have this header, and we learned earlier by looking at the RFC that the IPv4 header would be 32 bits across. It's 4 bytes, right? And how we read this is we start with the first row and work our way from left to right. And when we get to the end of that row, we then move to the next row and read left to right, just like we would a paragraph of text. So let's go ahead and read this paragraph here. The first 4 bits are the version number. So what would those, we've learned so much today. Let's go ahead and test our knowledge. And this could be a valid test question. If this is a version 4 header, what would those first 4 bits be? Oh, so close. Come on. Where is it? Where is it? Where is it? What's that? Not 0010. It'd be, check your math on that. It'd be 0100. Yeah, because that would be a 0 in the 8th position, a 1 in the 4. Oh, and then the rest would be zeros, right? Yeah, that's a valid test question. So for those wondering, well, what would be on the test? That could be one. What are the first 4 bits of an IPv4 header? You'd be like, wait a minute, what do you mean the first 4? How would I know what the first 4? Oh, because it is the version number 4. So those are the types of things that you would have to know in advance. And so remember, oh yeah, the first 4 bits is the version field. You could look this up, but you see those first 4 bits, say it's just version number, you then have to think ahead. Well, if it's v4, it would be the number 4, it'd be decimal 4. Okay, now let's move on to the next one. The internet header length is how long this header is. That particular field is not telling you how many bytes. It's actually telling you how many quad words. Remember that quad word name we used earlier where it was actually 32 bits? Isn't each one of these rows a quad word? So the internet header length will actually say 5 there, which means that's 5 rows long, unless there's options. IP allows us to use some other options. We don't get into that in this class, but if you want to buy me a beer down at the bar tonight, I'll tell you what all those options are. But for our intents and purposes, in our packet here, there's no options. And so that would say 5. So we've got 4 here. We've got 5 here. These next 2 fields are more router management on networks of DSCP and ECN. We're not focused on that so much in this class because from a security perspective, it actually doesn't really matter. Because how you route the packet from one location to another, I don't care. So those next fields after internet header length, it's just those are all set to zeros anyways when I send a packet and when I receive a packet. Let me go ahead and show you in Wireshark what I'm talking about. So let's go back to Wireshark here, and I am going to open up a different packet capture. We did ARP, we know what the IP addresses are. Let me go ahead and open up this conversation. I am going to go to packet number 10 in this conversation. We see some ARPs there, we see a DNS query, and then we start at packet number 10. We are going to analyze this packet, and it's layer 3 internet protocol. We see the version is 4. That checks out, that makes sense. And the internet header length is 5, and so that means that this is 20 bytes in length. It's 5 quad words. We see that DSF and ECN is not set. Those were all zeros. So notice the first 2 bytes of an IPv4 header just about always are going to be 4500. So it's kind of an easy way for me to tell where does that begin. So we got 4500, and then the next field is what's called the total length field. What total length means is this is the number of bytes that this packet is from the beginning of this header all the way to the bottom of the end of the packet, including all other layers. So it's just basically saying the packet stops here. Here's the end of the information. So I know when the packet has stopped. Now the next fields here, the ID tags and flags and fragment offset, we're just going to ignore that row at 301. Not too concerned about that. The next field is the time to live field. Doesn't that sound insidious? That sounds like some sort of a James Bond film. You know, James Bond in Time to Live. It's like, no, it's not like that. It actually, the time to live field is even cooler than a James Bond film. At least from my geeky perspective, it's cool. Because if you look at the RFC tells you this is the number of seconds that this packet is allowed to live on the network until it's killed, until it dies. Ooh, doesn't that sound interesting? And why do we need such a field like that? Now, let me go ahead and explain how communications on the internet works by showing you just a series of routers here. Let's say this is just a series of routers that makes the backbone of the internet across the United States. And they are in a mesh topology. That star topology is we're all plugged into the same switch on our subnet here. Here's a mesh topology where there's just arbitrary connections between these different routers because these different ISPs to the ISPs are just brokering traffic back and forth. So the question becomes, what's the most efficient route to go from computer at router A to computer at router P? So let's say A is in Los Angeles, P is in New York. How do we get this packet from Los Angeles to New York? There's multiple paths that it could take. So let's say I create this packet on computer A right here, and I send it to, I'm sorry, the computer connected to router A, shall I say. And so that computer sends it to their gateway at A. A is going to look at that IP address and say, oh yeah, I send those to E based on its configuration. And then E says, oh yeah, based on that information, I send those packets to H. H says, yeah, I send those to I. I sends to O. O sends to P, and the computer at the end will receive the packet. Awesome, that's the internet working efficiently. Now, what if Chicago at location I there, what if they're taken out by, say, a nuclear weapon? Boom, Chicago's gone. You should have seen the look on students' faces when I nuked Chicago in Chicago. So now, H can't send to I anymore. What is H going to do? What's that? Send it to J? Maybe. H is going to look at its route tables and say, oh, I can't send to I anymore. What's my default location? Remember, every computer has a default location. I send to my router when I don't know where that goes. Remember, with the US Postal Service, you don't know where it goes. You send it to the next sorting center and they figure it out. Well, what's that default location for H? H looks at its routing tables and says, oh, well, I can't send it to I. What's my default location? F. So it sent it to F. Now F receives this and says, oh yeah, I know where these goes. F looks at its routing configuration and says, every time I get packets destined for P, I send them over to E. Does E know where to send this packet? Yeah, sends it to H. Does H know where to send this packet? Yeah, to its default, F. Does F know where it goes? Yeah, to E. Uh-oh. We're caught in a routing loop. These routers do not pay attention to the packets that they've sent. That would take a lot of resources to say, oh, I've seen this packet before. No, they're just looking at the destination address and just routing it based on that destination address. So it does not realize it's seeing the same packet over and over and over again. Now this packet is immortal. It will not die, and it will stay on that network forever, or until I comes back online, or one of these routers configurations are changed. So how did they deal with these immortal packets before IP? What they would do is they'd shut off the routers of the network and just drain the network of any immortal packets. That wouldn't be very scalable on the internet today, right? Everybody at 5 p.m., turn off your routers. You're going to drain the internet of immortal packets. Yeah, that's not a good idea. And so they said, well, with IP, what we're going to do is create a time to live field. And in the RFC, it literally says, this is the number of seconds the packet is allowed to live on the network until it's dropped, until it dies. Now, when the implementers of the TCP/IP stack went to build their hardware stacks with TCP/IP on their machines, they go time to time. There's no clock on the internet. There's no master clock there. So how do we know what time it is? So the implementers, they said to the designers of the RFC, they said, you made a bad protocol. You need to fix this. The designers said, no, it's just, you figure it out. You're smart people. So they go, time. We don't have any time here. We can't count seconds. What could we count? Couldn't we count the number of routers that the packet has traversed? Wouldn't that kind of be an indicator of time? And so this time to live field actually became a router count. So now with computer attached to A, let's say they set this time to live field, the TTL, to, I'm going to choose an arbitrarily low number just for demonstration purposes. I'll show you what those numbers usually are. I'm going to set it to 10. So the computer connected to router A set the time to live field to 10. A receives this packet and before it forwards that packet on, it decrements that TTL to 9 and then sends the packet to E. E decrements that TTL to 8 and forwards it on to H. H decrements it to 7 and then sends it to F. F decrements it to 6. And now we're just in a countdown, right? 5, 4, 3, 2, 1. H sends the packet to F with a TTL of 1. F decrements that to 0 and says, ruh-roh, this packet didn't make it. And so F is just going to discard that packet. Oh, packet didn't get there? Does the sender know? Did we notify his parents? We didn't notify his parents? IP is like, that's not my job. That's somebody else's job. We'll talk about whose job that is. Don't worry, the parents will get notified, all right? But this packet didn't make it. So now we don't have to deal with immortal packets because there's no such thing as an immortal packet. All packets will, given enough time, given enough router hops, they will all either get to their final destination or they will just be dropped. So let's go ahead and talk through the rest of these fields here. Fix that. There we go. Extend. Let me check Slack and make sure everybody is good there. Rennie, thank you for remembering the OSI model. You could use the please do not throw sausage pizza away, or there's also please do not take salespeople's advice. Thanks, guys. So it's kind of a helpful mnemonic to remember those layers. Thanks for sharing that. Appreciate that. Now, let's talk about the protocol field. The protocol field is telling us what is the next header. Literally, this just means next header. What comes at layer 4? Since it's oh, I'm sorry. Do you know what? Before we move on to time to live, I forgot to mention something. So the time to live field you can see is a 1 byte field, which means that the number could be a maximum of 255, right? So what should we set that number to? Well, the RFC doesn't say. In fact, the RFC would say it was this number of seconds. So what did people set that number to? Different implementers chose different numbers. With the Windows operating system, modern Windows uses a TTL of 128. Mac OS is using 64. Earlier versions of Mac were using 60. Earlier versions of Windows was using 32. And now we see many Linux kernels were using 255. Now, question for you. If you receive a packet from an address on the internet and the TTL of that packet when you receive it is set to 120, are there certain operating systems you could rule out as having sent that packet? Could that packet have come from a Mac OS 10 machine? No, because they use 64. And remember, those routers count down from that number, not up. So I know that it couldn't have been a Mac. Now, are there some operating systems it's more likely than others to be? Is it more likely a Windows computer that was 8 routers away from me? Or is it a Linux computer that would be 135 routers away? Well, what is the average number of router hops across the internet? On average, you can get to any location on the internet in 13 hops. So I'd say 8 being closer to the number 13 than 135. It was likely 8 hops away, not 135. If you received a packet that had to go through 135 routers to get to you, that was probably inefficient. There was a problem there. That's not efficient enough. That's a bad design. So we're going to hang on to that information because later when we scan another computer, we're going to try to determine the operating system. We are going to analyze that TTL field and see what that value is, making some operating systems more likely than others. Rennie. Say that again. I'm sorry, I couldn't hear you. So Rennie is asking a question that we haven't gotten to yet. He mentioned a loopback address. We haven't talked about what a loopback address is. So in just a few slides, we will. And I will re-ask your question if I don't answer it then. Okay. I will answer it. We're not there yet. And I could tell you right now, but it wouldn't be valuable to the rest of the class because they don't know what a loopback address is yet. Great question though. We'll definitely cover that. So now, the protocol field is what the next header, what is the layer 4 header after this layer 3 IP header. And so if the protocol field is set to the number, let's say if it's set to 6, it means TCP is the next header. If it's set to 17, UDP is the next header. If it's set to 1, ICMP is the next header. And the reason I mentioned those three is we're going to talk about all three of those in just a little bit. But that's how we determine whether it's a TCP packet or a UDP packet. Now, the header checksum is a field that we don't even use anymore. It was just checking for unintended changes to the packet. But systems don't even bother looking at that checksum anymore. So we're just not even going to focus on it here. Then there's 4 bytes for the source address, 4 bytes for the destination address, and options if the IHL is greater than number 5. Here we've got those fields highlighted, but going back to our example, and every time I change screens with Wireshark, it does that. So let me fix Wireshark here. And open that packet capture back up. Go back to packet number 10. You'll see that total length was 52, which means this entire packet after the from the IP header all the way to the end is 52 bytes in length. Oh, we can see that the time to live is 128 exactly. Now that's very interesting. That's 128 exactly. And I'm going to guess, I don't know if I'm right, but I'm going to guess that this is probably a Windows machine that sent this packet. And when I captured the packet, it hasn't traversed any routers yet. That's a plausible story, right? Do we know for sure? Not yet. But there's some information here later where we're going to realize, yeah, that probably was the case. And so a Windows machine sent this packet. I captured it at the NIC of the Windows machine. So the packet hasn't traversed any routers yet. Okay, that's a theory. We'll test that. The next field is the protocol field. We can see that it's set to 6. And so therefore, we know that the next protocol is going to be TCP. All right, at layer 4, it'll be TCP. We've got 4 bytes for the source address or the sender's address. We've got 4 bytes for the destination. And as you can see, even though we humans, we use dotted decimal, where we've got 172.20.60.8. Well, in the packet, you can see those addresses are just simply in hexadecimal characters because it's just bits, right? It's just bits. Any questions about IP? It's pretty cool, huh? How it works. It's just a routing protocol. Given a sender and a receiver, how do we get that packet from the sending computer to the receiving computer? Now, in this header, did we see anything that looks like security? There's no security here as well. Earlier, I said, if you dropped a letter into the mailbox here at the hotel, letter carrier comes by and picks it up. Are they even going to look at the address, the from address, and see if it's the address at the hotel? They don't pay attention to that. Now, if there's no security here in IP version 4, couldn't I just make up any IP address there? Couldn't I make an IP address that isn't mine and put that in the packet? Could I send, we already discussed that Google's DNS server is 8.8.8.8.8. Couldn't I send a packet where it looks like it's coming from 8.8.8.8, but I sent it, not them? Yeah, that's very plausible. Is there any real way of detecting that that happened? No. So what must we assume again? Is that it is. There's no way to tell because it's just simply a packet that we received that says it's from 8.8.8.8. If I receive a letter that says it's from Publishers Clearinghouse and I just won, could evil Jake have sent that to me? Sure. I wouldn't know that it didn't actually come from Publishers Clearinghouse. Cool. All right. So no security again. Now, I know you were all worried about that packet. Remember the packet that died because its time exceeded in transit? What happened? What's the story? Were his parents notified? So IP doesn't care. The Internet Protocol doesn't deal with that. But that's okay because there is a helper protocol that's actually part of the same RFC called ICMP. It is a helper protocol for IP that allows us to report errors, allows us to report statuses on the network like ping. Ping is where you are going to send an ICMP packet to another machine that is what we call an echo request. I am going to send a ping packet to 8.8.8.8. That's an echo request. Hey, Google's DNS, when you receive this packet, could you send a reply back to me that you got it? Just so I know that you're there, I'm pinging you. When I get that response back, I know that you received it and I know that you responded. All right, so let's go ahead and take a look at what ping actually looks like in a screenshot. Screenshots aren't fun. Let's go ahead and do demos. Today is all about the demos. Why don't I show you ping in action? So I am going to ping 8.8.8.8. Too many dots. Take off the dot. There we go. And now we see responses coming back. I sent an ICMP echo request to 8.8.8.8 and I received a response. Yes, I'm up. I'm here. From 8.8.8.8. In fact, I got 4 of them. Why 4? Because Windows by default, unless you tell it otherwise, Windows always does 4 and then it stops. Whether they actually got responses back or not. Now, that is helpful, but notice there's also something else here that's interesting. Notice there's a TTL there in that ICMP echo response. That's a TTL that started at Google's 8.8.8.8. Now, could this indicate what operating system sent this packet? Yeah, there's some information here. What don't I know at this point? I know that I received the packet with a TTL of 48, but I don't know what they sent it as, right? Could I determine, is there any way for me to determine how many routers were between me and 8.8.8.8? Well, I would need to be able to trace the route. Trace route. There is a command like ping, where ping, I am just saying, hey, ICMP echo request, please respond with an ICMP echo reply. And then there's trace route, where I can send an ICMP echo request to another machine. But what I'm going to do here is I am going to manipulate the time to live field. What I'm going to do is I'm going to send a packet that's a ping packet going to 8.8.8.8. But I'm going to set my TTL to 1. Will a TTL of 1, will that packet get to 8.8.8.8? Not if I don't have a direct connection, a direct physical cable going to that server. It will not get there. Well, wait a minute. So what actually happens? So let's go ahead and do a trace route to 8.8.8.8. And what my computer is doing here is on line 1. This is an ICMP echo request going to 8.8.8.8, but the TTL was set to 1. My gateway going out of this network decremented that to 0 and said, oh, the packet didn't make it. Time exceeded in transit, and sent an ICMP packet back to me, said, sorry, it didn't actually get there. Oh, okay, but I know that IP address of the router because it gave me its IP address. And so then what do I do next? I send an ICMP echo request to 8.8.8.8 with a TTL of 2. My router, my gateway here, decrements that TTL to 1 and sends it to the next router. That next router decrements it to 0 and responds ICMP echo, ICMP time exceeded in transit back to me. So now I know the IP address of that second router. And so then what does my computer do? Sends an ICMP echo request to 8.8.8.8 with a TTL of 3. You guys get the idea here, right? And so what I'm doing is I'm tracing the route of the IP addresses that my packet has traversed. And actually, because I didn't tell Windows otherwise, Windows tried it 3 times. And so that's what these times are in 3 columns. Was I tried it once and twice and 3 times. And I got 3 responses back from each of those IP addresses. Now you'll see at router 6, the request timed out. Some routers on the internet just don't even play in this game. Oh, your packet didn't make it. Too bad. I'm not sending you a time exceeded in transit because I don't want you to know what my IP address is. So it just silently ignored those. And then we are now at hop 13. We're at 14. It's all timing out. We should be getting to 8.8.8 pretty soon here because then there we go. 14 hops away. The 15th was Google, right? So that seems to make sense because I said the average number of hops between 2 points on the internet is about 13 routers today. This only took 14, so that's about right in that average, no problem. The 15th was Google. Now, what if I took that 14 and added 14 to 48? What would I get for a number there? And I'm seriously asking you, I can't math right now. 62? That wasn't any of those operating systems on the list. Maybe Google has a proprietary operating system or they're setting their own TTL, or I don't know. In fact, do you know what's interesting about Google's DNS server? For one, it's not one server on the internet. 8.8.8.8 resolves to a different machine depending on where you're at geographically in the world. And when I was in London last week and we ran this, the TTL was entirely different. It was not 62. It was 124 at that location. So that tells me that for one, obviously, Google's DNS server is different from location to location, and there are likely different operating systems running Google's DNS server depending on where I'm at in the world. Interesting. So now I've traced the route. Let's now talk about this special address. Rennie wanted to talk about this address. Let's talk about the loopback address. The loopback address is a special IP address that doesn't route anywhere because the IP address for the loopback is your NIC. And it's my NIC. And it's your NIC. It's your NIC. I feel like Oprah here. And it's your NIC. And it's your NIC. And it's your NIC. Everybody stands and applauds and goes, yay, we all have NICs with IP addresses. Well, wait a minute. If we all have the same IP address, what good is that for? It's what we call the loopback address. My computer creates a packet going to the address 127.0.0.1, I send it to my NIC. My NIC says, oh, that's me, and sends it right back to me. And quite literally, if I were to ping my own NIC, I get these responses back, and the TTL is exactly 128, which makes sense because I'm a Windows machine here. I sent it to my NIC sends it right back to me. Rennie, does that answer your question? There's no routers in between with the loopback address. So I get the exact same TTL as I sent because no routers were involved. All right, cool. So I could use this as an address to access services on my machine. I've used a bunch of different software packages over the years. Sometimes I am running a web server on my local machine because I'm building an application on my local machine. And I just simply, instead of going to, whatever domain name.com, I am just going to 127.0.0.1 because that means me. I'm my own web server in that case. I'm just testing software. Cool. So let's talk now about what this means to our computers and their settings. So we've already talked about IP addresses. We talked about routers. Let's start putting all of this together. Your computer, in order to participate on the network, has to have at least 3 things. It needs to have an IP address that's unique on that network to that computer. It also needs something called a subnet mask. We'll talk about what that mask means to us and why it's important in a little bit. But it also needs to know the default gateway. In order for my computer to communicate out to the internet, I need to know the IP address of that gateway. If I don't know what the IP address is, how can I send an ARP request? Hey, what's the MAC address for my gateway if I don't know the IP address? So I program that into the computer. And you'll see in this example, we just have a graphical user interface, the window for configuring that IP address and the subnet mask and the default gateway. This IP address defines me on this network. The subnet mask is going to define the network. We'll talk about that in a little bit. And then the gateway defines how I get out of this network. I need to go to 8.8.8.8. So what is that path out of this network to 8.8.8.8? Now, your computer will almost always need to have a DNS IP address as well. And here we can see the DNS IP address is 1.1.1.1. That's a weird one. Yeah, it kind of feels like it's like 8.8.8.8, right? Does anybody know who the DNS server is at 1.1.1.1? That's Cloudflare. Yeah, so it's Cloudflare's DNS server. If it's all 9s, guess who that is? That's Quad 9 is the service. It makes sense, right? Because it's 4 9s and they call themselves Quad 9. So now, in the Windows machine, I can set these in the Windows configuration in the graphical user interface. In Mac, it's the same information. It just is in different places because there's a different OS and a different graphical user interface. And with Mac, the default gateway is called the router. And so you can see that router is the same as this gateway. It's not the same address. We're just showing you different settings on different machines here. Okay, cool. So far, so good. You got a question? Okay, you looked at me like you had an intent and you're like, okay, cool. You're just reaffirming everything I'm saying, right? Yeah, Matthew is giving me this nonverbal feedback. I get you. All right. I thought maybe that was in the form of a question. Like this difference between I get it and I get it. Yeah. I was like, I thought you were asking that as a question. All right. So now let's talk about the IP address itself. IP version 4 has a 32-bit address. IPv6 actually has a 128-bit address. So it's a much bigger address space, but we're just going to talk about v4 addresses here. With a v4 address, it's a 32-bit field, which means that we can have up to 4.2 billion addresses out on the internet. And each address is going to be unique to that computer on the network. And it's just bits according to the computer, but for us to understand it, because if you ask me what's my IP address and I say it's 110.0.0.0.0.0.0.0.0.0.0.0.0.0.0.1, you'd be like, what? No, come on. Let's make this easier. So I say it's 192.168.119.216 dotted decimal. And if you say it like that, the cool kids are going to laugh at you because we don't say the dots when we're cool. Yeah, no, we're too cool for that. So I'm just going to imply the dots. 192, 168, 119, 216. Why would I say the dots when they're just already implied? The only time the cool kids say the dot is when you need to for clarification. 192, 168, 32. Okay, what's the last one? 2. Oh, it's 32.2. No, it's 30.2. Oh, that's the only time that the cool kids say the dots, right? Or I have an address that's 10.1.1.2. Cool. So now this address, it feels like it's just simply a static address on the network when it actually has two different portions to the address. The address is going to define two things. It's going to define the network that the computer is on, and it's also going to define which host, which computer on that network. The question is, which part is that network portion of the address, and which part is the host on that network? That's where the subnet mask comes in. The subnet mask in this case is, and our network engineers set this subnet mask, and so that our computers know how large of a network it is, which portion of the address is the network portion, which portion is the host. And so in this case, they set the first 3 bytes to all ones, right? 255, 255, 255. Well, that's the highest decimal number you can represent with bits. And so those bits are all set to ones, right? So here we would see the subnet mask, the first 3 bytes would all be ones. And then you notice that last byte is 0. So that means all those bits are set to 0. And what that means for this IP address of 10.1.1.2, the network portion is the first 3 bytes of that address. So 10.1.1 is the network address. And then the 2 is the host on the network of 10.1.1. The best way I can describe that is to talk about my mother-in-law. Didn't think the sentence would end that way, did you? So now my mother-in-law, she's a little bit out there, but she's sometimes she has a stroke of genius in this little bit out there. She would mail a letter, and on the front of the letter, she would put this. You go ahead and duplicate screens. There we go. Drawing board. So now it's the front of the envelope. And of course, we have to have a stamp in the corner. So we got the little stamp there. And she would write this on the front of an envelope. And this is all that would be on that envelope. Is this being delivered anywhere? Getting a lot of people shaking their heads no. You know what? When I asked the US Postal Service, they said the same thing. They said, no, this isn't going anywhere. It is. It's actually being delivered. It's being delivered to the post office of the zip code 87111. And then it's going to PO Box 153 at that post office 87111. I know that for a fact that this works because that was my PO box in the Northeast Heights of Albuquerque, New Mexico. It's the same post office as Walter White. I live just on the street from Walter White, as far as that movie goes. And yes, the show goes. And yes, I saw filming crews. The JP Wynn High School that he taught at, all of the outdoor scenes were filmed in the parking lot directly behind my house. I could literally see them filming as we were watching just out our backyard window. And it was kind of fun. Just a side note. When Skylar White would come home with Albertsons grocery bags, I was like, yeah, I know what store you got that from, because it was, if they were real people in real life, I would have run into them at the grocery store at some point, because our grocery store was the same. So this is his post office as well. Now, I know that this works for a fact because I received this in my PO box one day. So it does work. Now, the Postal Service, those people, they said, wow, you surprised me, because we just didn't think that would have been enough information to be, for it to be delivered. But why am I telling you this in class? What does it have to do with networking? Well, instead of being a PO box and a zip code, why don't we change the conversation? Isn't this 87111, isn't that the same as, say, the network? Isn't your local post office like your local network? And that your delivery point, your address, would be the host on that network? The way that mail routes in the US postal system is they get it to the zip code first, and then the post office that services that zip code sends it to the delivery point. So absolutely that zip code, totally lost. I was going to say area code for a moment there, but that's phones, right? That zip code is your network, and your street address is the host on your network. And so that's what we see here in our subnet mask, is it's telling us which portion is that zip code, which portion is the IP address, and then which portion, the rest of it, is that host. Now, I know, Rennie, you had questions earlier. I want to make sure that I answer those. So this is that time to ask those other questions. I forgot what the question was. Were we going to talk about subnetting? Yep, so we're here. And oh, by the way, one other thing before I move on these slides is that you can program your computer to have the subnet mask, and in this case, it's 255.255.255.0, but on a network map, using that subnet mask numbers on a network map that's got a whole bunch of networks, that's going to be kind of clunky and weird. So rather than using a subnet mask on a network map, what they'll do is they'll put a slash and then 24, like with this network address 10.1.1.0, and then it would be a slash and then 24, which means that these first 24 bits, or the first 3 bytes, that's the network portion. So that slash 24 just basically means the network is defined by the first 24 bits. And then the question is, well, who determined this? Your network engineer, the person who designed the network, they're the ones that decided how big the network was going to be. And we use that information in our computer to determine whether these computers are on the same network as us or a different one. So now we've got a sending computer. 1.1 is sending to another computer. 1.2, this is the sender on top, the receiver on the bottom. What I'm going to do is compare these two addresses bit by bit in those first 3 bytes, because the subnet mask said the first 3 bytes are the network portion, and it's all same. It's all the same. So what do I know about those 2 addresses? They are on the same network. Now, let's make that receiving address some other address. In this case, it's 3.1. So I'm sending from 10.1.1.1 going to 10.1.3.1. Let's say our subnet mask is the 3 bytes. So I compare bits, same. Whoops, this 1 bit is different. And all it took was 1 bit. Those are two different bits there, which means that it's not on the same network as me. So I can't send it directly to them. I have to send it to my gateway. By definition, then, got a question for you. And it would be fair to ask a question like this on the exam. Does the gateway of your network have to be, does its IP address have to be on the same network as you to send to it? Absolutely. Because we wouldn't be able to send it to the gateway if it was someplace else, because what do we need is a gateway to send it to someplace else. So now I've determined, is it on the same network or different? That allowed me to answer that question. Is this computer on the same network as me? The answer in this case was no. The computer answered its own question by looking at its IP address and the IP address of the destination and compared the two based on the subnet mask. It said if it's the same, yes, the answer would have been yes. But in this case, the answer was no, because those two systems were on two different networks, because that bit right there, and all it took is one bit, was different. That tells us it's not on the same network as each other. So I have to send it to the gateway. That brings us to that gateway. All right, so this gateway is my outlet to the rest of the world. If I am sending a packet from, say, 1.1 to 1.2, I would just simply do an ARP request. Hey, who is at 1.2? Tell me your MAC address. And I'd send it through the switch directly to their MAC address. Well, if they're on a different network, I need to know who my router is. I am going to do an ARP request from my machine. Hey, what is the MAC address to the router? Everybody gets that question. The router responds, I am at that IP address, and here's my MAC address. So then I forward the packet to the MAC address of that router, and then they handle it from there. Now, what we're going to do, and notice this router's IP address is on the same subnet as all of these machines. It has to be. Once when I was at the University of Colorado, I received this email. It was part of an email chain that was just going back and forth, and they were CCing me because this networked device had to do with PCI compliance. It was a payment card machine. And so I was getting those emails just simply because I was the internal security auditor, the ISA for PCI compliance at the university, at least for that campus. So they were CCing me back and forth on these on this email exchange. And it was somebody at the university was communicating to somebody that was the vendor, the seller of that piece of equipment. And the vendor sent them these network settings. And the person said, the settings aren't working. The machine's not communicating on the internet. Now I saw the emails go back and forth. I was just, okay, that's interesting. They'll figure it out. And it kept going back and forth. So I looked at the email once and I said, hey, yeah, something's not right here, because they had an IP address and a subnet mask in a default gateway. And based on those settings, I could tell they were invalid, that they would never work because they had the gateway outside of the network. According to the subnet mask. It's like, yeah, no wonder your settings aren't working. They are literally invalid. That's why your device wasn't participating on the network. Your router was outside your own network. So therefore you can't send to it. So now this default gateway is the gateway of last resort for each one of these locations, where I put the letter into the mailbox. The postal worker that came by to pick up that letter, they don't know where it goes. So they send it to their default gateway, the post office. The post office doesn't know where this goes. They sent it to their default, the sorting center. And the citywide sorting center in this multi-state mail, the citywide sorting center for Los Angeles sent it to San Francisco. San Francisco sent it out of California because they don't know where it goes. So each one of them were using their default gateway to get out to the internet. And that's literally what you see here. using our trace route is going back to these IP addresses. My default gateway is 192.168.0.1. Their default gateway was 192.68.1.1. Their default was 172.22.0.1. And so you guys see that here we got default gateway to default gateway to default gateway, and then out of the hotel's network, and then out on the internet. All of those routers on the internet said, yeah, we're not going to respond to these requests. Good luck with that. We're not going to tell you what our IP addresses are. But we basically, oops, sorry, was I off the camera? For folks online, if I talk with my hands a lot, do you know how you could shut me up? Tie my hands behind my back and I wouldn't be able to talk. And so every now and then I'm waving, I'm doing this, and this camera's going crazy because this is the hand signal for train the camera on me. And this is also the same hand signal for to take the camera off of me. And so here I am talking, the camera's constantly, what do you mean? What, am I supposed to follow you? I'm not. So sorry if that happens. Cool. So now I go default gateway to default gateway to default gateway out to the internet. And then we have that mesh topology where the backbone of the internet is going to further and further get that packet closer to its final destination. But that's how I got out to the internet, is by using those default gateways. And there can be multiple ones. The Denver router here at that region-wide sorting center, I don't know if you guys caught on, but I'm going to repeat myself now so that you can catch something that I said differently at that point. When we were talking about the mail, I had said the local post office says, I don't know where that goes. So I send it to my sorting center. And I said, the sorting center said, I don't know where that goes. So they send it to their sorting center. That sorting center says, I don't know where that is. So they sent it to Denver. Now at the Denver region-wide sorting center, I said something different. I said, based on that address, the Denver location says, oh, I know where that goes. That goes to Texas. So we were default gateway, default gateway, default gateway. I don't know where it goes. 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 And then Denver says, yes, I do know where it goes because I've been told I send mail routed to Texas. I send all of that mail to the sorting center in Dallas. So Denver actually knows where it's supposed to go. Now, in our network diagram, each one of these networks had a default gateway. So this one was the default gateway for network 1. This is default gateway for network 2 that we didn't really define here. This is the default gateway for network 3. And then that intermediate was the default gateway for these default gateways. And then if the intermediate doesn't know where it's supposed to go, they use the internet, their ISP, as their default gateway. So that's that default gateway to default gateway to default gateway. Now, but Tim, you got
organizing and what is that model? Do ISPs stay into that, or like how does that?
Tim wants to know about that backbone of the internet. Who's in charge of that? Those ISPs to the ISPs. UUNet, Hurricane Electric, Sprint Communications, Level 3 Communications. Those are some of the providers in the US. And then other parts of the world, they have their own service providers as well. And so you pay your ISP for your internet connection. Your ISP takes some of that money and they pay them. And then they say, hey, I will pay you to transfer 1 billion bytes of data. And here's a price for that. And that's literally what that least cost route is. I said it's geographically getting closer and closer. And I'd like to think it's the most efficient route. But in reality, it's whatever is the cheapest route money-wise for that ISP. Because if they're charging you 70 bucks a month for your internet access and they can pay less than that, they make money. And so they're going to find the cheapest way to get this traffic out to the internet. Now, between companies like UUNet and Hurricane Electric, what they'll do is rather than exchanging money with one another, One of them will say, you send me 100 million bytes of data and I'll send you 100 million bytes of data. We'll just exchange that. And so that's how they broker that traffic back and forth, is that they don't pay each other. They just make agreements. Yeah, I'll send a bunch of data to you and you can send a bunch of data to me, and it all comes out even in the end. And if you end up sending more data than I do to you, then I'm going to bill you for it. Great question. Love the questions like that. Now, let's talk about how routing works. With routing, I am basically trying to get this packet to its final destination based on that IP address, and some router somewhere needs to know where that location is. In this case, my intermediate had what's called a routing table in it. The routing table is just a list of network addresses and interfaces physically on the device for those ranges. So let's say this is just a standard networking device. It's a hub, which isn't a switch or a router, but I'm using this as, and yes, I traveled with this device so I can hold it in my hands. Like I said, I talk with my hands, and so I got to hold stuff when I'm showing you. So I feel like a prop comic, like I'm Gallagher or something, right? Here's a prop. Let me show you how it works. So now let's say this is a router. And in this router, I have a list in RAM that says, for all packets destined to network 1, put it out the network 1 interface. For all packets destined for network 2, put out the second interface. All packets destined for network 3, send it out this interface. For any other packets, send it out the gateway. The fourth one is my connection out to the internet. So for all IP address ranges where I know the IP addresses, I know which interface to send it out. If it's not listed in that routing table explicitly, then I send it out to my intermediate and I say, you guys figure it out. I have my own default gateway. So the network engineer has put this table in there so that they can send it to each of the network's gateways. And then each one of those gateways also know that their packets going to their internal network goes out that internal interface, and that all packets leaving that network goes out the external interface. Cool. So now we can route packets from one location to another. Now let's talk about how that looks like as far as default gateways and routing on our network diagram. We went from system 2 on network 1 to system 2 on network 3 by using the default gateway to our network. Our network's gateway used their default gateway, but now this intermediate that was that control point, they look at their settings and look at that route table and they say, oh, based on that IP address, that falls into the range of network 3. So they route it. This isn't a gateway now, they route it to that router. And network 3 gateway says, oh yeah, that is my IP address range. And so I route it directly to system 2 at network 1. Now, if my intermediate gateway doesn't have defined what the IP address is for that particular route, it'll send it out its default gateway. That was the interface 4 on this machine that I had here. So going back to big picture on the internet, it is default gateway to default gateway to default gateway, getting out to the backbone of the internet. And then from there, it routes, getting to its final destination. Any questions? Well, I'm sure we probably have lots of questions. One of the things that will make a lot more sense to you later is after class this week, read the books. Now that we've got the context and the story, read the books, read all of that text to get the big picture. And then after you read the books, re-listen to this recording, and all of it's going to become clearer and clearer every single time. It's like going to the optometrist where, you know, they switch all the lenses and it's like clearer until we get to a clear picture. Right now, you're looking at a letter and you're like, that could be a letter B or could be a letter D. You're squinting. I understand that's where you guys are at right now. And that's fine. That's perfectly normal. The fire hose is turned on for a lot of you at this point, but it's time for us to take a break. So let's go ahead and take a break. When we come back, we'll talk about layer 4 communications and continue to work our way up the stack. Now, when we left off yesterday afternoon, my son, 14 years old, he says, Mom, Dad, I want to become a goalie. And we said, we support you in whatever you do, son, but you're not going to learn how to be a goalie over a summer and play at the same competitive level. And then he proves us wrong by working his butt off and gets a spot as a goalie on the same team. You're then going to notice after the first video, yes, in the first video, he's wearing orange 82. And then he says, Mom, Dad, I want to take this even further. His first season as a brand new goalie, he was a month into the season, he was the #1 goalie in the league by save percentage and finishes that season winning the state championship for the team in the net as a rookie. So he's going someplace with this. He jumped after that, jumped 2 skill levels with a different team, was playing AA hockey his second season as a goalie. And so you're going to see him switch to a different jersey number. He's going to be number 33 after that when he was 82 before. So go ahead and enjoy the hockey action. I will see you all back here in 20 minutes.
Secret that you keep on every time I'm told, I'm just another soul to sell. Oh, well, it's out of hands. I'm the face that you have to face, mirror in your stare. I'm once left, I'm once right, I'm the enemy. And I'm gonna take you down and you through your knees. So Lie, you're getting better all the time and turning up against one isn't it's hard to change. Another type of words that's often unsuspecting hurt, and as you step back in the line, a march up to that beat. Now dance, make her dance, make me dance, dance, With the thousand lights in the sky, between slowing out a line and drifting closer in your sight, so play it right away. It's a scene about me. There's something in your way, and now somebody's gonna pay. And if you can't get what you want, well, it's because of me. Now dance, but good dance, man. Now we're gonna change. The thousand lights in the sky. Chance, and no one, it was really some dance, I never chance, it was really with the thousand lights and I get to the sky, between say one that was taken down. Two ways another. Cross you fail. The stuff that's hard to things are changed. No one knows I've no love. No strangers singing in your name. I'm changing the back sides. Let's say we take this town. No king or queen of any state. Get up to shut it down. Open the streets and raise the dead. I know how to scale. I know what to feel without a face. Get on without a care. Before it's way too late. Baby, it's season. I'm changing about these skies. Oh God, I'm still moving. Falling through hell. Everything For every piece to fall in place, forever gone without a trace. You're the rise and takes its shape. No turning back, don't turn that page. Come now, breathe it in. Come now, let's leave it all. And through hell, I'm feeling happens over. Long as the room keeps singing, that's just the business I'm in. I digress. Not painting no trash, you sleep, all the boys who the dance floor didn't love, and all the girls who couldn't move fast enough, sing until your lungs give out.
Wow, well, that's a lot of fun there, isn't it? So let's go ahead and get back to business here. What we've been doing is we've been working our way up the protocol stack. We have covered layer 2 MAC addresses. We have now talked about layer 3 IP addresses in the internet protocol. We're going to continue to work our way up the stack, and we're going to talk about layer 4 TCP and UDP. Now, we know that a packet is either going to be TCP or UDP by that protocol field in the IP header. Remember the protocol field, if it was 6, it means that's TCP is coming next. And if it was 17, that's UDP coming next. 1 was ICMP, and we already covered ICMP. Now, at layer 4, we have this notion of services on a network that is determined by a listening port. Now, a listening port, when I say port, it has nothing to do with the ports that were on our networking devices. Forget about this device. That's not the kind of port we're talking about. What we're talking about here is a software port. It was just a designation, a number, so that the computer knows logically what the port it is, or what port is, not physically a port. Now, with your network ports, we numbered the first 1,024 ports as well-known ports. We said anything 1023 and below is a well-known port. And so things like port 80 and port 443, port 110, those are all well-known ports. If I send a packet to your web server, port 80, I am saying port 80 is where I expect to talk HTTP, Hypertext Transfer Protocol. Or if I send it to port 443, yes, I want to talk HTTP to you, but before we do it, let's go ahead and encrypt. And so it's HTTPS for security. Or if I'm sending an email, I'm sending it to your port 25, SMTP, Simple Mail Transfer Protocol. Now, we figured that there would be no need for 1,000 different ports on the internet. Would there be 1,000 different services? No, how could that be? Turns out we blew through those really fast. Like, whoa, wait a minute. Not only are there 1,000 services on the internet, there's more than that, and they're growing every single day. People come up with new types of services that they want to create a server that provides the service. And so we need a different numbered port for that so that our machines can keep track of those services through the port numbers. So they said, let's go ahead and reserve a whole bunch of addresses for what we call registered ports. The registered ports list is 1024 through 49151. Well, that feels a little weird. What the heck is up with that number? Well, whenever you're looking at decimal values, and we're talking about networking, if those decimal values seem strange, they seem weird, if you map them out in binary, they always make sense, because every port number above 49151, starting with 49152, going all the way to 65,535, with all of those, let me go ahead and flip forward a couple spots here. Starting with 49152, the first 2 bits of those 2 bytes are set to 1s, which makes it very efficient for a computer to determine, is it high ephemeral port number, or is it lower than that? Well, let's just check those first 2 bits. If the first 2 bits are set to 1s, we know it's a high ephemeral port number. Ephemeral is just a fancy word that means temporary. It's just a temporary port that I open up to listen at. So now services listen on these well-known ports and registered ports, and then I contact that server at its IP address at one of those ports. If it's listening at the IP address, I'm telling that server, hey, I'm contacting you 443. 443 means that I want to talk HTTPS to you. And if that server is listening at that port, I would expect that there should be a web server at that port. and that web server is able to negotiate an encrypted connection with me before I start sending data. So if that server has 443 open, we're going to assume we can do HTTPS communications there. But they are going to send a response back to me. I requested a web page. They need to send the response back to me now. So what I am going to do is I'm going to send to their port 443 because it's open, it's listening, but I need to open up a port on my machine. I'm not a server. I am just a client machine that's asking for a service. And so I am going to open up a high ephemeral port number like 49152. I just chose the first one available. And so what I'm going to do is I'm going to listen at 49152 and tell them, when you respond to my web page request, respond to my 49152. And so that I know that that's related to this request I just made. So now from my IP address and my port number to their IP address and say port 443, we have now created what they call a network socket. This network socket is how I manage the communication flow during that session. Remember at layer 5, that session layer, it was keeping track of when does the conversation begin? When does the conversation end? Now we're going to talk about maintaining this session. We're going to call it a socket. A network socket is just basically 2 IP addresses communicating with 2 port numbers. So I've got my computer at 10.1.1.1, and I'm going to contact a server at 7.7.7.1. And let's say I am going to connect to their service that is port 80 HTTP. I send a packet from my IP address and my ephemeral port number, 49152 in this case, to their IP address at port 80. And when they respond, this is now a network socket. Okay, and now we can maintain this session on this socket. But then my computer also sends another request to that server, same IP address, but in this case, I'm asking for a different service. I want to do HTTP, but I want to encrypt this one, so I send it to their port 443. So now I choose another high ephemeral port number, in this case 49153, to their 443. So they respond back to me from their IP address to my IP address and port number. So now we have a second socket. And then let's say I start sending an email. I initiate sending an email, so I contact their machine port 25 SMTP, and I choose another high ephemeral port number. So now I have 3 different network sockets, all to the same IP address. And as long as we're using different sockets for each of these, I'm sorry, let me start that sentence over again. As long as I am using different port numbers for each socket, our computers can keep track of these 3 different simultaneous connections because I've got 3 different sockets. Now, what if my computer is actually initiating 3 connections to the same service? Each one of those is to port 80, their HTTP communications. Have you ever opened up a web browser and surfed to a website? You're at their web page, and then you open up another tab and you surf to the same website? You ever wonder how your computer keeps track of those different tabs that are open? And Michelle's saying, well, I never thought about it till now. How does that work? It's okay, Michelle, we've got a solution for that. We have 3 different port numbers on our machine going to that same service. But when you get the responses back from one of the tabs, it goes to port 49152 on your machine. The next one could be 49153, next one's 49154. So, okay, I'm able to manage 3 different simultaneous connections to the same service at port 80, and I'm able to keep track of them because I'm using different port numbers for each one. Now, these port numbers are used at layer 4 for the 2 main workhorses of the internet, TCP and UDP. TCP stands for Transmission Control Protocol, and it's what we call a session-oriented protocol because it will maintain the state of communications. Some would say that it guarantees packet delivery. It can't. Can I guarantee, could TCP force a computer to receive a packet if that computer's off? No, it can't guarantee that. More accurately, what TCP does is it's going to attempt to send this data and will resend it and will continue to do so until the recipient responds that they've received the data. That's all TCP does. MJ.
So, the computer is off, so if I'm sending an email, definitely go to the server, that's directly to the computer, right?
Yes, so MJ asked the question, well, what if I'm sending an email to somebody whose computer is off at that point? That email actually goes to their email server. And tomorrow at the end of our encryption conversations, we're actually going to talk about how email works. But I'm not sending an email directly to their computer. I'm sending an email to their server, and their server is going to hold on to that until they check their email. Yeah. So with transmission control protocol, it's going to manage the state of that connection. And if data was not received that I sent, what I'm going to do is I'm going to attempt to send it again. You still didn't get it? Let me try it again and try it again. Okay, it worked this time. Great. Let's go ahead and continue on. Now that's TCP. UDP stands for Unreliable DAM Protocol. User Datagram Protocol. It's not unreliable. It's just not guaranteed. There's no session. There's no connection between the two computers. It's what we call a best effort protocol, like IP is a best effort protocol. Did it get there or not? I don't care. Wasn't paying attention. UDP is the same way. Did it get there? I don't know. Did I send a packet? I don't remember doing so because I didn't keep track. So with user datagram protocol, UDP, it takes a lot less overhead because we don't have to set up the session for one. And that's fine, as long as some packet loss could be acceptable. And in some situations, UDP is actually superior to TCP. We'll actually, we have to use UDP instead of TCP, depending on the type of connection. But we'll talk about what that looks like after we talk about the two of them. Let's start by talking about TCP. The TCP header simply is 2 bytes for the source port, so that's the sender, 2 bytes for the destination port, that's the receiver. So that was our high ephemeral port 49152 going to port 80. Those 2 numbers are there. And then there's a sequence number and an acknowledgement number. I am going to use those numbers to keep track of whether data was sent or not. Let's go ahead and go back to our Wireshark example and talk about some of these fields. Where's Wireshark? Here we go. Oh, that's right, because I changed screens and Wireshark messed up. Let me go ahead and restart it. Let's go back to packet number 10. That's the one we've been talking about here. So here's packet 10. And I know that this is a TCP packet because remember in the protocol field in IP, it was the number 6, which means TCP is the next header. So let's go ahead and open up that TCP header. And we see that there's a 2 byte source port and it's a high ephemeral port number. And the destination port, the destination port here is 443. So the sender was a high ephemeral port. The receiver is a web server, right? Now going back to something we talked about in the IP header, remember what the time to live field was set at? It was set at 128, right? Which is indicative of a Windows machine. And now this kind of validates, yeah, it's starting to feel more like it's a Windows machine because remember, most workstations are Windows workstations and Windows workstations use web browsers to communicate to web servers. And so the fact that this TTL is 128 and that it's a high ephemeral port number in TCP, it's really starting to feel like this is communications from a Windows computer to some sort of a web server. Does that make sense? So far, we still don't know for sure, but we're kind of putting together this picture. MJ, are you all right with that? Or it looks like your face has a question, but I'm not quite sure I'm picking up on that. Going with the flow, just following things along. Any questions about how I determined that this is likely a web browser client machine contacting a web server? So the destination port 443 means we're looking to contact an HTTPS web server, yep. But that high ephemeral port where it's above that 49.152, this one is 61.063, that feels like it's a client machine. There's no services up at port numbers that high. So it's really starting to feel like this is a Windows machine that is contacting a web server at port 443. Yeah. And notice, so far we've made those determinations and I've got a pretty high level of confidence now seeing this layer 4 header that this packet is part of a communications that was captured on a Windows machine as it left the Windows machine. Because that TTL was exactly 128, and because this is a high ephemeral port number to a web server, it just feels like that's a Windows machine contacting a web server. Do we know what the operating system of the web server is right now? I don't know that, but I do know I've got a good idea of the operating system of the machine that sent this packet. Now, we can see that there is a sequence number that was set by this computer. And we'll talk about that sequence number in just a moment. But it is a 4-byte, really large number. And it's basically saying, let's start our conversation here at this point. This computer just chose a number and said, let's start here with that number. There's also an acknowledgement number field that's also a 4-byte number, and that's set to all zeros right now. The reason it's set to zeros we'll discover in just a little bit. The next fields that I want to talk about here are let me go ahead and change this, are these fields right here. They're what we call the TCP control bits or the TCP header flags. With these header flags, they are 1-bit fields. So if the field is a 0, it means that field is not set. If that bit is a 1, it means that field is set. And we've got a few different ones here. We've got urge, which is for urgent, which means this packet is more urgent than the other ones. It's like sending an important email. You know, the people basically ignore those now. It was a good idea, poor implementation, because of course all packets are urgent. Why not? Now, the next field I want to talk about is this push. If the push field is set, what that means is during normal TCP communications between two computers, if I have a TCP connection open to another machine, it might be more efficient for me, since I know that this connection is still open. Maybe I'm going to wait to get more data before I process what I've gotten so far. So I put that data that I've received so far into a buffer, and I'm waiting for more information to add to that buffer. And then once that buffer is full, I send that up to the processor to process this data. But sometimes we don't want the other machine to buffer it. Go ahead and push it up the stack for processing. What that means is, hey, in the middle of this connection, you may have buffered some information. I'm asking you to take whatever you got so far and the information in this packet and just go ahead and push it up the stack for processing. During communications of my computer to a remote machine, if I am interacting with that machine at, say, a terminal window where I have like this CMD window that I opened up here where I'm communicating with my machine, imagine this is actually a remote connection with another machine, and as I type, I want to be able to see the characters, keystrokes. I am going to be sending packets to that other machine saying, hey, go ahead and push the information up for processing because I want to be able to see that I've typed those characters. So then they send me a response back. Yep, you typed those characters. And so we're pushing the data for processing. Otherwise, I could be hitting keys on my keyboard and I don't see anything on the screen because it's just buffering the information, right? So that's what that push is there for. Now, the other ones are all about setting up, maintaining, and tearing down a connection. So there's the SYN flag. The SYN flag means I want to synchronize with you. And then there's an acknowledgement flag. The acknowledgement flag is I acknowledge that you sent me data. I acknowledge the packets you sent me. Then there's also the fin flag. That means I want to finish the connection with you. But there's actually two ways to finish the connection. I can either finish with a fin flag, or I could reset the connection with a reset. There's different reasons to use those. All right. So now let's talk through what we see in Wireshark here. Here's our example in the slides, but what I want to do is show you here in Wireshark that this particular packet has the, let's see here. Oh, I see what I'm trying to find. Here we go. So here, if I expand this out, you'll see that the only bit that's set, all of these are all zeros. The only one that's set is this SYN, which means I want to synchronize with you. Well, what does that mean in communications? Is this the beginning of the connection, the end of the connection? Let's go ahead and talk about how TCP communications works. With TCP communications, I am going to start by sending a SYN packet to the server. And so the SYN flag is set. Oh, just like the one we looked at. Yeah, that's a SYN packet. Now the server is going to respond with a SYN ACK. With this SYN, they're saying, yeah, we'd like to synchronize with you as well. But now this acknowledgement is them acknowledging my original SYN. See, I went all biblical on you, acknowledging the original SYN. Yeah, those are the jokes at this point in the day, folks. Those are the jokes. Now, since they said they want to synchronize with me, I send an ACK back, a single ACK that says I am acknowledging your synchronize. Great. And then I can send them a request. I initiated this TCP connection, so I'm going to send this request. Hey, I've got a request, send me some data here. And the server is going to then respond, here is the data. And the acknowledgement flag, the ACK flag is set for each one of these. And so it starts SYN, SYN-ACK, ACK for the first three packets. And then it's ACK, 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 ACK back and forth. If I go back over to Wireshark, we're going to notice packet number 10 had the SYN flag set, and that was the only one. And then we see there's the going back from port 443 to the high ephemeral port number. So the return trip from the server, they sent a SYN ACK. And then I send the final ACK. So there's those three packets, SYN, SYN-ACK, ACK. And now we see ACK, ACK, ACK after that. And in fact, oh, here's a push. There's one of those push packets. And I can see ACK, 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 ACK back and forth. We are communicating two ways. Now, while that two-way communications is going on, we set those sequence numbers. Remember that sequence number in this packet was a very large, let me go back to packet 10. Go back to packet 10 and notice this number was set to, it's a 4-byte number and it's a very large number. My computer just arbitrarily chooses a large number. And that's the starting point. of my sequence. When I sent a synchronized packet to you, I sent you a sequence number. And what I expect the server to respond with is the following. They're going to set an acknowledgement number, and that acknowledgement number is going to be a combination of the sequence number. And I'm just going to choose an arbitrarily low one, so it's easy numbers here. Let's say my sequence number is 500. And then I sent you 100 bytes of data. What they're going to do is they're going to take that sequence number and add 100 to it to represent the 100 bytes of data that they've received, plus 1. So it's the sequence number plus the bytes plus 1. And so they would respond to me with 601. When I receive this acknowledgement number of 601, what do I know about the data? I know that they received that 100 bytes of data, because otherwise, if they didn't receive the 100 bytes of data, they would have sent me 501 because it'd be 0 bytes. And I know they didn't actually get the data, so I would retransmit. That's what TCP is all about. Retransmission of the data if it wasn't acknowledged as being received. Now, going back to Wireshark here, I started with this sequence number. That was a high number, and notice it ends in 5057. Just remember 5057. And you're going to see that in the second packet, we see SYN-ACK, and you'll see that that number, that acknowledgement number, Wireshark says that it's 1, because what we've got here as the acknowledgement number is 5058. Now, I was synchronizing with them. I didn't put any data in the packet. And so the fact that they said they didn't receive any data from me makes sense. So they just sent me my sequence number back to me with an acknowledgement number of my sequence number plus 1. So I know that they got my packet. I know that they got that. Let me try that again. I know that they got that packet because they mirrored my sequence number back to me in that acknowledgement number. But now notice the server also set their own sequence number. They set it to, at the end here, it says 6612. Now, if we go to that ACK, that final ACK here, packet 12, you'll see that I am acknowledging 6613, which means they haven't sent me any data yet. We're just setting up the connection at this point, right? No data has been transferred, but now we're in synchronization. Our sequence and acknowledgement numbers are all matching up. I know that you received every packet that I sent you, and you know that I received every packet you sent me. If any packets were lost, we would be able to detect that because those numbers wouldn't make sense. And so we would retransmit any data that wasn't received. All right, cool. So now we can keep track of the data going back and forth. We're doing ACK back and forth. Send me some data. Here's the data. ACK, I acknowledge I received your data. Good. Now let's say all good conversations have to come to an end eventually, right? And so at the end, I am going to send a FIN packet to you. You are going to respond with an ACK back to my FIN. I am saying, I want to finish this conversation. I'm done asking for information. And so let's go ahead and gracefully tear down this connection. And then the server, you're going to respond with a FIN packet as well to me, and I respond with an ACK back. So literally with TCP communications, 10 packets minimum in order to set up the connection, just ask for data and then tear down the connection. Now going back to our Wireshark conversation, you're going to see that we did SYN-ACK, ACK, and then ACK, push ACK, back and forth. And then you see at the end of the conversation, there's FIN and ACK and fin and ACK. The conversation has now ended. All right, cool. And that's how TCP communications should work. Everything worked as expected. Nice. The question is, why in the world did it take us 4 packets to finish this connection when it only took 3 to start? Any thoughts on that? Why did it take 4 packets? It only took 3 to create the connection. Why would it take 4 to end it? Go ahead. I'm going to take what Matthew said, I'm going to condense it and say what Matthew is trying to say here, and I'm going to oversimplify what you said there. All good conversations start at the beginning. They start where I say, hey, let's synchronize, let's talk. And so 3 packets where we can just exchange those sequence and acknowledgement numbers. But not all conversations end at the same time. And so when I send you my fin packet, I say, I'm done talking to you, and you acknowledge that. And then that end of the connection is terminated, and I'm not sending you any more data. But let's say you're a web server, and my request for the data was I want a JPEG image, and that JPEG image is 10 megabytes in size. Well, 10 megabytes will not fit in a single packet. Ethernet packets have a maximum size of 1500 bytes. So you will have to send me lots of packets to send all of the data. And so I say, send me image.jpg FINAC. I'm done asking for it, but you're still sending me packets. We're still keeping track of your end of the connection, even though I tore down my end. So then when you're done sending that data, then we do FINAC. Yeah, Michelle.
Two sequence numbers, you have to close both.
I'm sorry, say that again.
You had 2 sequence numbers, and so you have to FINAC both of them.
I do have to FINAC both the sequence numbers. Yep. But the main reason we have to do it in 4 packets instead of 3 was literally because the connection doesn't always end at the same time. Somebody over here had said something, or are we good? Aaron, you had an answer, or you're good? Okay, I thought somebody over here said something. All right, cool. Now, that is a graceful termination of the connection, FINAC, FINAC. What if we need to reset that connection because something's not right? I can't finish the connection doing FINAC, FINAC because that's just, something's not right. The sequence and acknowledgement numbers are out of whack. I'm sending you a sequence number and you're sending me an acknowledgement number that doesn't even make sense. Or you sent me an ACK packet and we didn't have a connection going on. So I send a single reset and we've ended the conversation. There's no need for you to acknowledge it. We just stop talking. Now we could start talking again by doing SYNCINEC ACK. But if I send a reset packet, there's no need for you to acknowledge that. It's just conversation's over. Whoops, and my camera isn't following me here. Let me go ahead and fix that. There we go. So that's TCP communications. It's keeping track of the connection. We have a start to the conversation. We then exchange data. We acknowledge the data that we've received, and then we finish the connection. But it's a lot of packets that does that. With UDP, there's no need to set up that connection because there is no connection. I send you a packet and I never know if you received it using UDP. I don't know if you got it or not because I'm just simply sending from my source port to your destination port. That's it. There is a length field for how long the packet is after that. And there's a checksum that we don't use anymore, just like we saw in IP. But there's not a whole lot to deal with here. There's not a lot to break. So it usually just works fine. I don't know whether you received it or not. I don't care. UDP doesn't care. So how a UDP packet would look is, let's say a client machine just sends a request to the server, hey, send me some data. An example of this would be a DNS query. We're going to talk about DNS in just a little bit, domain name system. And I'm just simply sending one packet. Hey, I need to know the IP address for a domain name. And so I just send it in one packet as a request. You receive it and you respond with one packet as a reply. The IP address for this domain name is, and you give me an IP address. So one packet for the request, one for the response. There was no need to set up that whole connection, SYN-SYN-ACK. Hey, what's the IP address for this domain name? Here's the IP address, FIN-ACK. That's a lot of work, a lot of overhead there. UDP doesn't have much overhead. Now, sometimes it's just a matter of a machine sends one packet and we don't even need to send any response back. For example, we were talking yesterday about having a central log server. The central log server is collecting a lot of logs from you. And so let's just send one log, a message in each packet. Here's a log, here's a log, here's a log, here's a log. And wait a while. Oh, here's another log, another log, another log. Wait a little while, another log, another log. There's no need to set SYN-SYN-ACK. Here's a log, FIN-ACK, FIN-ACK, SYN-SYN-ACK. Here's a log, FIN-ACK, FIN-ACK. That's a lot of overhead. So when would we use UDP instead of TCP? When there's excessive overhead that's created by TCP, like those log files, we are not going to use TCP, we're going to use UDP. But there's also cases where UDP even makes more sense, like in real-time communications. Like this conversation here with everybody in Zoom, this is a UDP conversation between our computers, because my computer is just sending packets to you in real time as I'm talking and as video is flowing. And with real-time communications, we would not want to resend any data because it wouldn't make sense to do so, because it wouldn't make sense to do so, because it wouldn't make sense to do so. It wouldn't make sense to do so. There, you see what I mean? There, you see what I mean? There, you see what I mean? Yeah, you guys get the idea, right? There's no reason to retransmit because that point in time has already gone by. So we're going to use UDP. If I'm on a voice over IP phone call using UDP and the packet gets dropped, the humans do the retransmission. They say, hey, I didn't quite hear you there. Can you say that again? So why would we have it retransmitted? Humans will just manage that retransmission. Now, the third case here is where there's repetitive data. I'm getting similar data over and over and over again. If I miss one of those packets, no big deal. Like network time protocol, NTP. With NTP, you set up a central time server for all of your users on your local network, and you're just going to tell them the time. That's not like an internet clock that doesn't exist. This is for my local network, where I'm just basically sending out the time. The time is now. Next packet, the time is now. The next packet, the time is now. And in fact, if I use TCP, that would be bad because for one, it'd be SYN-SYN-ACK, the time is now. Wait a minute, the time isn't now because the time was the time when we started the conversation, but some time has gone by. And in fact, with TCP, it's even worse because if a packet is dropped, we retransmit it. And that's a really bad day because it's no longer that time. I don't want it retransmitted because now it's too late. Your computer has a clock on it. It's not going to stray too far. So if you miss a packet, no worries. There's another one coming in 8 seconds anyway. You'll be fine. Now, the fourth case is where we have one-way connections, a data diode for a sensor. Imagine I have a sensor that is so important that the data is accurate. This is an integrity issue. Where it is, let's say it's a thermometer measuring the temperature of a core of a nuclear reactor. Now, if an attacker was able to hack that sensor and make that sensor report the wrong temperature, things go exploded when stuff like that happens. And so I want to make sure this is completely unhackable. I am going to literally clip the physical line that allows that sensor to receive any information. I have made it unhackable at that point because an attacker can't get to it because they can't send anything to it. It can only send data out. Well, I can't do TCP because you can't do a three-way handshake without two-way communications, right? So UDP is the only way I'd be able to do that with this one-way connection. And then the fifth one is for multicast traffic. Multicast traffic is different than broadcast. Broadcast earlier is where we set the MAC address to all ones, all Fs, and everybody gets a copy of that packet. Here with multicast traffic, I am going to send one packet to multiple IP addresses. TCP cannot support multicast traffic, but UDP can. And so I send one packet with multiple IP addresses. The router receives this packet and says, oh, this is meant for 5 different IP addresses. And so it creates 5 copies of that packet and sends it to the 5 different locations all at the same time. Now that time component is why this multicast traffic is important. Imagine you are a brokerage house and you collect data from the New York Stock Exchange to make trades. And if your data that you're receiving isn't timely, if you receive the data too late, you receive it later than other people could be reacting to that data and you haven't reacted yet. You're losing money because time is literally money in this case. I could not do, let's say U6 in the inner row here, you're all brokerage houses, your buildings are near the New York Stock Exchange, and you all have connections over the network to the stock exchange. And as the stock exchange is sending data, I am setting up TCP connections. So it's SYN, SYN-ACK, ACK. Jose, here's the data, FIN-ACK, FIN-ACK. Kelly, SYN, SYN-ACK, ACK. Here's the data, FIN-ACK, FIN-ACK. Rennie, SYN, SYN-ACK, ACK. Here's the data, FIN-ACK, FIN-ACK. Jake, SYN, SYN-ACK, ACK. And meanwhile, Michelle is like, WTF, I'm not getting any data here. And Jose here is already acting on that data. That's not good. So multicast traffic, where I send one packet to all 5 IP addresses and you all receive it at the same time. Now, I've got a story for you that's used to be an unsourced story. As I was telling you so far this week, every story that I've told you is absolutely true. I have a source for it, including Steve Crocker sitting on the toilet writing RFC number 1. That's a true story. This story I'm about to tell you used to be an unsourced story, and story that I heard that this is the case, but couldn't substantiate it through a news article or any person that I heard, any first person story. I didn't hear this first person. I don't have a news article for you. So it's something that I heard. I believe it to be true, but it doesn't have a source. The story that I heard was with the New York Stock Exchange. Each one of these brokerage houses, though they are near the New York Stock Exchange, some of them are a little bit further distance down the road than others. So now let's say Jake here, he is 100 meters down the road. Jose is right next door. Well, that even though communications flows at almost the speed of light, there still is delay between when Jake receives it and when Jose receives it, because Jose is closer than Jake is physically. So what they would do is they would, regardless of the distance that you were away from the stock exchange, all your cables were the exact same length, which means if that cable that connects me to Jake, if that cable is 100 meters long, guess what Jose has spooled in his data center? 100 meters of cable spooled in the data center. So our cables are the exact same length. And so that's fair. Everybody receives the data at the same time. Now, I was telling this story just a couple years ago in Chicago to a class, a 301 class. It was before we nuked Chicago, right? And so I'm telling this story in Chicago, and I said it's an unsourced story. Now, after class, one of the students, she walks up to me and she says, that thing that you said about the cables, she says, that's true. I know that that's true. And at first I was interested. I was like, so you have a news article or something? It was some source. I was like, really? How do you know? She says, because I'm the auditor of those cables. I wanted her autograph at that point. It's like, this is amazing. You audit the cables? All right, you're my source. And she said, yeah, and those cables are audited down to 1 centimeter of tolerance to one another. That's how close it has to be. It's like, cool, that's neat. So UDP is what we'd have to use there. TCP wouldn't make sense because I want all 6, in this case, all 6 of them receive that data at the exact same time. And even a few microseconds in delay can cost companies. There's been articles written on this. A few microseconds in delay can cost a company millions of dollars over a year's time just by a few microseconds of latency. How's everybody feeling about TCP and UDP? You guys all right? Good? Ready to continue on and finish out our day and then do our lab? Okay, so before we move on, a TCP packet walks into a bar, says to the bartender, I'd like a beer. The bartender says, a beer? He says, yes, a beer. I'd tell you a UDP joke, but I don't know that you'd get it. All right. So come on, TCP packet walks into a bar, says to the bartender, I'd like a beer. A beer, yes, a beer. It's a 3-way handshake. Okay. Those are the jokes at this point, folks. Matthew's good over here. All right. We are rocking it, guys. So what we've got now is we've got 3 more services that we're going to talk about on the internet. I like to call this the layer 7 section because of some of the application layer stuff. We're going to discuss HTTP. We're going to discuss SMTP and all of those later. But there's a few layer 7 services that need to exist in order to make the internet usable. So let's talk about those 3, and then we'll go ahead and finish our day with the lab. Now, the first one to talk about is DHCP, stands for Dynamic Host Configuration Protocol. When you guys joined the network here on the SEC 301 hotspot, you entered your necessary settings, right? I gave you an IP address and you put them in your machine. I gave you a subnet mask and a default gateway and you put them in your machine. You guys don't remember doing that, do you? Because we didn't actually do that. When you connected to the SEC 301 hotspot, you just got settings and they worked. Where did those settings come from? DHCP. You joined the network, and instead of statically setting those IP addresses, like we saw earlier in the Windows example, instead of setting them manually, what you did is it just was working for you. So DHCP dynamically assigned you an IP address. So now you've got a lease on an IP address. We say this lease time is time in hours or days. Here's an IP address and settings. Use that for the next 24 hours or the next 7 days. And so you use that for that set period. And if you still need to participate on that network after that, after say 24 hours, you're going to ask DHCP, hey, I had these other settings, but I've lost the lease on that. It's expired. Should I continue to use these settings, or are you going to give me different settings? And so DHCP manages that. Now, the whole point of DHCP originally was for efficient use of IP addresses. Because remember, we only have so many IP addresses. And what if I have a network where I've got 254 usable IP addresses, but I have 300 people that work at this company? I would have to assign them to some people to use for a period of time. And then when those people left, let's say I've got people working in 3 shifts throughout the 24-hour period. So shift 1 comes in and it's 100 people come in, they get 100 IP addresses. And we tell them use those IP addresses for the next 8 hours. And then when they leave, I've got another people come in and they ask for IP addresses as well. I give them IP addresses from the pool of addresses, and then they use those for 8 hours. And another group comes in And then they need 100 IP addresses. Now we're at 300 IP addresses, but I only had 254 available. That's okay. By the time shift 3 gets into the office, shift 1 has already released those IP addresses back to me. So it's efficient use of the IP address space. But then it turns out there's other benefit, like I don't have to tell you guys what your network settings are. You just set it to DHCP and the DHCP server gives you the settings. So what that looks like on your Windows machine is you would just choose obtain IP address automatically. That means it's set for DHCP. With Mac, you would simply just choose using DHCP and you would get your settings from the DHCP server. Notice on a Mac, if it's manual, we can see the IP address and subnet mask and router are editable fields here. You'll notice when you choose DHCP, they're not editable, they're grayed out. And the same with Windows. If I set obtain IP address automatically, I can't put numbers in here. But if I choose use this IP address, I can put the settings in. So it's just based on which radio button I click. You guys know that those are called radio buttons, right? The circles. You guys have all heard that. Does anybody know why it's called a radio button?
No, it's like one at a time. It's only push like an 8-track, like button or whatever.
Like an 8-track. So Michelle is saying, she says, when I was a little girl, my grandfather had this big old Oldsmobile. And then this big old Oldsmobile had a radio where you would have to turn the dial to get to the radio station. And that the radio had these programmable buttons where once he finds the right radio station, that's the one I want, he pulls that button out and pushes it all the way back in. And now that button is programmed to that spot on the dial. And what happens when he chooses a different radio station from those presets, let's say he's got 5 of them, he presses one button in, what happens to the other buttons? Those pop out. And that's exactly how these work on the computer, where if I press this button, that one's going to unselect. Isn't that cool? That came from, that's where they got the name radio button. And so now you know the rest of the story. And yeah, that was, if you didn't get that reference, you're too young. All right. So now about the radio button and saying, now you know the rest of the story. Tim got it. Yeah, Tim's showing his age there. It's like, yeah, it was after school special. No, that was from, what's his face? Not Walter Cronkite. It's, darn, okay. Somebody's typing, somebody's going to get it here. Let me. Paul Harvey, that's it. Yep, Paul Harvey. Very good. Maureen got it. Thank you, Maureen. She got it. Now, Michael says, how do you find out who was doing something evil, stuff on the computer when the internal IPs change? Anyway, to pin it back to a specific user for a specific time. Great question there, Michael. For one, we know that IP addresses can be spoofed. I could put an IP address in a packet that wasn't my IP address that was assigned to me. But also, here's another problem. How would you know when somebody is doing something evil based on their IP address if those IP addresses change over time? Michael, the answer is you don't. That IP address is not validation that somebody, so I'm looking for a criminal with criminal intent. IP address is not strong enough evidence to say that was the person that did it, because I know IP addresses can be spoofed and I know that IP addresses can change over time. The way that I would pin it back to a specific user is some other form or fashion. The most common is that I assign everybody accounts and they log in with their account name. We'll talk about some different types of authentication management later when we talk about wireless and things like that, but you don't. The IP address isn't good enough. Now, let's see, Rennie said, I think it might be trickier if the machine was shared because the multiple actors, so they would be able to have access to that MAC address. So Rennie, let me go ahead and burst your bubble even further about this. IP addresses can be spoofed, so can MAC addresses. Your MAC address is burned into your NIC, so it follows your NIC wherever you go, but that can be changed by software. And in fact, with Android operating system, with Mac, with Windows, all of those operating systems allow you to do something called randomize your MAC address. Because if my MAC address is the same on my phone as I'm walking down the street and I'm walking past all of these Starbucks coffee locations and each one of them has a Starbucks access point, well, if my Wi-Fi is turned on and they see my MAC address for my packets, whether I'm interacting with their access point or not, they see my wireless packets on my phone just simply because they can. It's in the airwaves. And so couldn't Starbucks track me around the world because my MAC address is always the same on my phone? That's a privacy issue. So I can set the setting on my phone to randomize the MAC address. What that means is as I am traveling around the world, sending out these signals wirelessly, my phone keeps changing its MAC address. So question then becomes, when we're trying to find evil Doc, would we be able to trust any of the information? Can we trust that it's the right MAC address? No. Can we trust the IP address? No. None of those are strong authenticators. So again, we're in the same situation we were before. These protocols were built with insecurity, no security. Go ahead.
Figure out why we. So, you know, we established earlier that it could provide the topic. So, like, for example, if you could type 0 and then give me 250 code.
Mm-hmm.
So, obviously, you know, there are least time chip work, but if you need more code on that net at one time, is that when you could use static IP and figure yourself in
So Rennie said a lot of words there. So let me recap for everybody online. First, the conversation was about, well, when would we use dynamic or static? And let me answer that question first. So almost always, and it's not a hard and fast rule, but almost always client machines, like here in this room, we're using DHCP because it's just easier to manage it that way. And now, when would I use static IP addresses? Is for my servers. The server's IP address doesn't normally change, and I don't want it to because I want people to be able to find the server. And so I will set static IP addresses for servers and dynamic IP addresses for clients and hosts. So with DHCP, the DHCP server will have a pool of IP addresses that nobody else is using, and they are the only server that assigns those out, and they know which addresses are available. And so it's a pool of addresses. Now let's ask the next question. You said, well, what if I need more IP addresses? I only have 254 for that subnet. I need more. Well, my network engineer could simply change the subnet mask to a larger range of IP addresses. They have to be available to me, but I set a larger set a smaller network portion, so it's a larger host portion. And so if I simply just add more bits to the host portion, I can have more computers. And so let's say I set the subnet mask to 255.255.0.0. Now I have 2 bytes for the network and 2 bytes for the host. And so now I can have 65,534 addresses available. Yeah, so I increased that range. But as you said, the network engineers will determine that.
or here?
And at your home network, your network engineer was basically the person that sold you the device because your settings are already set. And what's that? And we are going to, so just a preview of what we're going to do in lab on day 4 is we are going to configure a wireless access point, and the settings would be in there where we can set our range of IP addresses. Yeah, so I'm my own network engineer. But most people, they buy their access point and it just, there's enough IP addresses allocated to where you don't need to change those settings. Yeah. Great questions. So let's go ahead and talk about how that DHCP service works. I've got a client machine that joins the network. So your computer joins the SEC 301 access point and says to the server from UDP port 68 to UDP port 67, broadcast everybody, hey, is there a DHCP server here? If there is, the server responds, yeah, I am. How can I help you? And your computer asks for its settings, and then that server gives you a lease on that configuration. DHCP has many different configuration settings, but most of them are no longer used. Mostly DHCP is just for handing out IP address, subnet mask, default gateway, and possibly a DNS server. Now, question becomes again, what if I get more than one response back from a DHCP server? Which one am I going to believe? Just like ARP, it's the first one. So now Jake, instead of doing an ARP cache poison attack, what he does is he sets up a rogue DHCP server. And if somebody says, hey, is there a DHCP server? He says, I am. And Kim says, I am. Well, if Jake answers first, I'm going to ask Jake, what are my settings? And so Jake could literally then just give me an IP address that's his IP address on the network. And he says, I'm your gateway and here's your IP address. So there's 2 different ways to attack that. Again, it's only on the local segment that this is going to work. That doesn't work over the internet because DHCP is just not an internet sort of thing. Now, the next service that's necessary is DNS, Domain Name System, also known as Domain Name Service, where I need to resolve a domain name like Amazon.com or SANS.org to a numeric IP address. I have to, because what goes into those IP layer 3 headers are numeric IP addresses. The domain name doesn't go in there. So I need to know, what is the IP address for Amazon.com? What is the IP address for SANS.org? And how that works is my computer, I open up the web browser, I type www.sans.org, I hit enter. Now there's a resolver on my machine that's going to attempt to resolve that domain name, www.sans.org, to a numeric IP. And so then the first place the resolver looks is in the local cache. Have you been to the site recently? If you have, it's still in the cache in RAM. And so it's just going to use that IP address because it already knows the answer. And then if it's not there, it's going to check a special file on that machine that is called the hosts file. The hosts file is where you can just plain text put a bunch of IP addresses and domain names, and so you could hard code DNS entries right into a file on your computer. If there's an entry in that file for that domain name, they use that IP address. If there is no entry for that domain name, then we have to ask outside. Outside of the network, you have a outside the machine, you have a DNS server. So then you send one packet, port 53, UDP to your DNS server. Hey, what is the IP address for sans.org? Now, your DNS server may or may not know the answer. There's no DNS server anywhere in the world that knows all the domain names and all the IP addresses for every system. It just doesn't exist. So if your DNS server knows the answer, it's going to send that answer back to you. Great. What if your DNS server doesn't know it? Your DNS server has a DNS server. And so it's going to ask its DNS server. And that DNS server is going to ask its DNS server until we get back to the originating location of, oh, sans.org is at this IP address. And so then your DNS server receives this response from somewhere in the chain, and then it remembers that in its cache for a period of time. Maybe the DNS settings for that IP address was remember this IP address for 24 hours. So now your DNS server is going to hang on to that for 24 hours. And then it returns the response to you. So your machine is just going to keep track of the information it needs to keep track of. Your DNS server keeps track of the information it needs to keep track of. And somewhere along the line, we find the answer. Again, there's really no security here at all. There's no authentication of that DNS server. It's all plain text and no authentication. So this could be attackable as well. We'll talk about the attacks against DNS later this week in our attack and malware section. Now, if you have not set your DNS server in your settings, you are using your ISP's DNS. And so basically you're asking your default gateway, hey, what is the IP address for? And your gateway is going to do that query for you. Now, I can set my DNS server settings to Cloudflare or Google or OpenDNS or VeriSign. There's also DNS servers out there that are called family-friendly DNS servers, where they act just like a normal DNS server unless somebody tries to resolve an adult website, pornography, violence, hate speech, things like that. We can set the DNS server to a family-friendly one that doesn't resolve any bad content, so kids aren't being exposed to websites that they either shouldn't go to or didn't intend to go to. And then there's also DNS servers that won't resolve IP addresses to known ad servers. We're going to learn on day 5 that when you surf to a website and you see ads on a page, almost always those ads didn't come from that server that you got the page from. Those ads are coming from another server. Your computer is going to resolve the IP address for that domain name for that ad service. Well, this DNS server doesn't respond with any valid IP addresses for ad servers. The box for the ad still shows up on the web page, but the ad doesn't load because you couldn't actually get to that server. Rennie. So Rennie is asking, is that an updated list on that OpenDNS Family Shield? Yeah, so they update those on a regular basis. And so when new websites, new domain names are created, they make a determination as to, well, is this family friendly or is it not? And known bad websites get blacklisted and known good sites get whitelisted. Yeah, good question. Now, let's go ahead and talk about this problem on the internet that I framed the problem. I didn't address the problem and nobody called me out on it. At the beginning of the day in this morning, we found that 4-byte addresses gave us 4.2 billion possible combinations of IP addresses. But I also said that there are more than 5 billion people on the internet. How do we have 5 billion people on the internet if there's only 4.2 billion addresses available? And the problem's even worse than that, because most users have more than one IP address because you got more than one device. I've got an IP address here for this laptop. I've got an IP address here for this phone. Normally, sometimes I have an iPad sitting next to me here. I'd have an IP address for that. And then all of you, I see many of you have computers and phones. Some of you have 2 phones. It's been my general observation in life that the more cell phones somebody has, the less they smile. There might be a correlation. There's a correlation. I don't know if there's a causation there, but I know the most unhappy people are those that have 3 cell phones. See 3 cell phones on somebody's desk. I point at them, I say, I'm sorry, and they say, yeah, I know, yeah. So we've got a lot of IP addresses used here. How do we manage to have billions of people, more than addresses available? Well, the long-term solution was IPv6. With IPv6, a much bigger address space, 340 undecillion addresses, and that's a real number. We'll talk about how big that number is tomorrow. But how do I, with IPv4 being the most commonly used protocol on the internet today, how do I have billions of users more than addresses that I've got? Well, without network address translation, NAT is solving the problem. Before we get to NAT, let's talk about what the problem is without NAT. If I have 1,000 people trying to get out to the internet, I've got 1,000 computers, I need 1,000 IP addresses for the internet. So each one of them uses one IP address. Now with network address translation, and this is just one type of NAT, I have 1,000 people going out to the internet, but they're all sharing one IP address. So now I've got 1,000 people just using one. All right, well, how does that work? First, we have to talk about, somebody mentioned earlier in Slack, and I said, we talk about this later. They said, well, that address that I was showing you on the screen, is that a private IP address? What they meant is that one of the addresses in the ranges that we have defined as for private internal use only? So on our internal networks, we can use these addresses. So RFC 1918 defines anything that starts with 10 dot is a private IP address. That means that it's not routable on the public internet. And then 172.16 through 172.31, that's also a private range. That's one is less common than the other two. 10 dot is the most used, followed by 192.168 dot whatever. What that means is I can have a 10 dot network here in this room, and I could have a 10 dot network at home. You can have a 10 dot network at your home, which means in theory, we would all be using the same IP addresses over and over again. Wait a minute. I thought all IP addresses needed to be unique on a network. Yes, these IP addresses that are private are not routable on the public internet, which means that your 10 dot address on your network cannot route out to the internet. It just can't. It's internal use only. And the same for this network. This network, we can use 10 dot on the inside, but we can't use it out on the internet. All right, so how do we communicate out on the internet if we're using internal IP addresses? That's where network address translation with port address translation comes into play. I have an internal IP address. It's a 10 dot address, and I am sending a packet to a server out on the internet. My NAT device, which is almost always my firewall, is going to take the IP address for my machine, and it's going to pull that IP address out, and it's going to replace it with the firewall's IP address. But it's also going to pull my port number out, 49.152 in this case, and it puts all of that in a table and then assigns me a new port number. So it's removing my IP address and my port number and replacing it with one of its own. So my firewall is spoofing my IP address? Yeah. Remember earlier I said there's no security checks? And that wasn't a bug, that was a feature. It has to spoof your IP address. Otherwise, you won't be able to communicate on the internet. So that's why the protocols weren't changed, because they couldn't be. It just works this way. It's a feature, not a bug. So now, when that server responds, they respond back to the firewall's public-facing IP address that is routable on the internet at their port 6500. When we receive this packet from the server, The firewall is going to say, oh, 6,500. Yeah, that was the IP. That was for Doc at his IP address and his port number. So they take that information out of the table and they replace their IP address with my original IP address. They replace their port number with my original port number and sends it back to me. And it's completely, the whole process is transparent to me as a user. I don't see any of that. I'm just communicating out to the internet using my internal IP address, and they're sending packets right back to me. I don't see that that's going on unless I actually look. Let me show you NAT in action. So I have an IP address here of, check my IP address. You are all going to do this in the lab in just a little bit. So I'm demoing this for you. I'm going to ask my computer with IP config. I'm going to say, hey, what are my network settings? And we can see that I have the IP address of 192.168.0.152. But that's not how the internet sees me. I'm going to open up a web browser and I'm going to surf to a special web server that's going to report my IP address to me, the IP address that they see me at. And so let's do IPv4.icanhasip.com. I love icanhasip.com because I love the meme. I can has cheeseburger. I can have IP. I can has IP. I'm sorry. So now my internal IP address is 192.168.0.152, but out on the internet, my IP address was NATed to 50.207.7569. Okay, that's NAT in action there. And so the internet sees me at that address, even though I'm using this internal IP address on this network. That allows us to reuse IP address space over and over again. Now I can have billions and billions and billions of people on the internet using only 4.2 billion total addresses, because thousands of people can be using the same single address. So now, let's say I open up a second connection at port 153 going to that server. This NAT device is just going to assign another port number. And so we can keep track of that return traffic to 6501, gets forwarded back to me at 49.153. And then say my wife's computer goes online and goes to the same site. She chooses the same port number as me because we just arbitrarily chose the same number. That's okay. The NAT device will keep track of each IP address in each port, and they'll just assign a new port number to each person. So what we're going to do now is we are done with our section in networking, and now we're going to do a lab in networking. When you are done with the lab, lecture's done for the day. So please take a moment to fill out the evals. Thank you, thank you, thank you for filling out evals. And there's one every, Rennie's like, there's one every single, yeah, we are going to ask you to fill out an eval every single day because quality is, what's that? Yeah, what Rennie's going to put in his eval today is stop sending evals. And tomorrow we're going to send him an eval asking him how we did. Yeah. We just want to make sure to head off any problems. And so if folks are happy, then indicate that you're happy. If there's any challenges, we want to be able to remove those challenges. It helps me reading all of these comments to see how students are responding. And I'll actually use, even if I don't address your comments that you put in evals in class, I'm remembering what you guys said about the content during the week, and I use that to adjust how I teach this to you guys. So absolutely, those comments are very valuable to me. Now, when you're done with the lab, you're free to go, and Jake can burn book number 2 now. Just get rid of that one. We don't need that for the rest of the week. You doing what? You're gonna put them in what? Oh, a plaque. Oh, you're gonna mount the book in the shadow box? Nice. All right, so you will not need book number 2 for the rest of the week. Tomorrow, when you're done with the lab, you're free to go tonight. Please fill out the evals. When you come back tomorrow at 9 a.m. Eastern time, bring book 3 and your workbook, your laptop, and And close, please continue to wear clothes. All right, folks, I'm gonna stay in the in-person classroom as long as you guys need me. Folks online, thank you so much for a wonderful day 2. Sean is here to help you in Slack. We are going to be shutting down the Zoom session, but we'll still be here on Slack to help you guys out. And so feel free to reach out to Sean. He'll be able to help you with labs. People in the in-person classroom, I'll stay here as long as I'm needed. You folks have a good night, and I will see you tomorrow. For those who are interested, we have a keynote presentation tonight. And at the keynote is being presented by Dr. Johannes Ulrich. Whenever Johannes Ulrich speaks, you listen. He's got some really interesting things to say. He is he runs the Internet Storm Center, which is a threat intelligence collection agency that's actually sponsored by SANS. And he is going to be talking tonight as keynote about what's new and current threat debrief. All right, cool. If anybody knows, he knows, because he runs the Internet Storm Center. Have a good evening. For folks online, you can register for that at the SANS.org website. For folks in person, make sure to wear your badge, because you'll need your badge to get in. I'm signing off to Zoom. Folks will be here on Slack to help you out, and in the in-person classroom. Have a good night.